Hello there, and welcome to Life Beyond Seen, where curiosity slows down just enough to breathe and complex ideas are allowed to unfold at an unhurried pace. Tonight, we are travelling to a place most people will never stand, a place so remote that even maps seem to hesitate at its edges. We're heading to the very bottom of the world, to the vast white expanse surrounding the South Pole, and to a quiet question that has lingered there for decades. Why do scientists still avoid certain areas near the South Pole? It sounds dramatic at first, maybe even suspicious. After all, Antarctica is a continent dedicated to science. There are research stations, international agreements, aircraft landing on ice runways, satellites mapping every kilometre from above, and yet, scattered across that enormous frozen land are regions that remain largely untouched. Areas that are marked, logged, acknowledged, but rarely entered. Not because they are forbidden in some cinematic sense, but because they are complicated, risky, unpredictable, and sometimes simply not worth the cost of trying to understand them too quickly. If you pause for a moment and picture the South Pole, what comes to mind? Endless white, a flat horizon, a cold so severe it feels theoretical. But beneath that image lies a landscape that is far less simple than it appears. Ice that moves, ground that is hidden, weather that does not negotiate, and distances so vast that help, if needed, may be days away, assuming the sky allows it. Before we settle deeper into this frozen subject, I'd like to know something simple. Where are you listening from right now? Is it warm where you are? Is it night? Early morning? Are you wrapped in a blanket, or is there sunlight outside your window? It's interesting, isn't it, that while we talk about one of the coldest places on Earth, you might be somewhere completely different, in a room that feels safe and familiar. Two entirely different environments connected by a quiet thread of attention. If you find this exploration calming or intriguing, if this slow descent into polar mystery helps you unwind at the end of your day, I'd appreciate it if you gave the video a like, maybe subscribed. It helps this quiet corner of science reach others who might also enjoy drifting into complex questions without the usual rush. Now, let's move gently toward the ice. Antarctica is often described as a desert, and that surprises many people. A desert, we tend to think, must be hot, sandy, wind-blown. But technically, a desert is defined by precipitation, not temperature. And Antarctica receives very little snowfall in many regions. The interior, especially near the South Pole, is astonishingly dry. What snow does fall rarely melts. It accumulates slowly, compressing over centuries into dense ice that can be more than 3 kilometres thick. 3 kilometres of ice. That's nearly 2 miles of frozen history pressing down on whatever lies beneath. When we talk about scientists avoiding certain areas, it's important to understand that this is not about fear in the cinematic sense. It's about logistics, safety, preservation, and sometimes uncertainty. The South Pole itself hosts the Amundsen Scott Research Station, operated by the United States. Researchers there study astrophysics, glaciology, climate, and atmospheric science. Aircraft bring supplies. Equipment hums steadily even at temperatures that can drop below -70 degrees Celsius. And yet, travel just a few hundred kilometres away from established routes, and the situation changes dramatically. The first barrier is distance. Antarctica is vast, larger than Europe. The South Pole sits deep within the continental interior, far from the relatively more accessible coastal research stations. Moving across this terrain requires specialised vehicles or aircraft equipped for extreme cold. Even then, conditions can shift without warning. Winds can rise quickly, reducing visibility to almost nothing. Snow can drift across crevasses, creating deceptive surfaces that look solid but conceal vertical drops tens of metres deep. Crevasses are one of the most significant dangers in certain regions near the pole. They form as glaciers and ice sheets slowly flow over uneven bedrock. The ice cracks under stress, creating deep fractures. Some are visible, open gashes in the ice, Others are covered by thin snow bridges that appear stable until weight is applied. Scientists mapping these areas often use ground-penetrating radar to detect hidden crevasses, but radar equipment can fail, batteries can freeze, and interpretation is not always perfect. Imagine navigating a landscape where the ground itself may not be what it seems. Every step calculated, every route pre-scanned. Even then, uncertainty remains. Then there is the cold itself. Machines struggle in temperatures below -50 degrees Celsius. Fuel thickens. Hydraulic systems slow. Metals contract and become brittle. Electronic components can malfunction. Even simple tasks like changing a glove or adjusting a cable become difficult when exposed skin can freeze in minutes. Certain areas near the South Pole are avoided not because they contain something mysterious, but because the margin for mechanical error is too small. If a vehicle breaks down far from a station, rescue may be delayed by weather for days, and weather in Antarctica does not always provide warning. Katabatic winds, for example, can descend from the high interior toward the coast with remarkable force. These gravity-driven winds accelerate as cold, dense air flows downhill. They can reach speeds over 100 kilometers per hour. In some regions, these winds are predictable. In others, particularly near uneven terrain beneath the ice, their behavior can be more erratic. Whiteout conditions can arise quickly, erasing the horizon. Sky and ground blend into a uniform brightness that disorients even experienced polar explorers. In such conditions, scientists rely heavily on GPS, but near the South Pole, satellite geometry becomes challenging. Because most GPS satellites orbit at inclinations that favour mid-latitudes, signal distribution near the poles can be less optimal. While modern systems compensate for this, accuracy can still fluctuate. In isolated areas without established infrastructure, even small navigation errors can compound over long distances. There are also environmental reasons for avoidance. Beneath the Antarctic ice sheet lie subglacial lakes, hidden bodies of liquid water trapped under immense pressure and insulated by thick ice. One of the most well-known is Lake Vostok, buried beneath approximately 4 kilometers of ice. Reaching such lakes requires drilling through ancient ice that has been undisturbed for hundreds of thousands, possibly millions of years. Scientists approach these regions cautiously, concerned about contaminating pristine ecosystems with modern microbes. The decision to avoid or limit activity in certain areas is often based on preservation. Antarctica is governed by the Antarctic Treaty System, an international agreement that designates the continent for peaceful scientific use. Environmental protection protocols restrict activities that could cause irreversible harm. Some regions are designated as Antarctic Specially Protected Areas. Entry requires permits, and access is limited to minimize disturbance. In other words, avoidance can be deliberate stewardship rather than fear. Still, the psychological dimension cannot be ignored. Prolonged isolation in polar environments affects cognition, mood, and perception. During the Antarctic winter, the sun does not rise for months. Temperatures drop further. Aircraft cannot land in complete darkness and extreme cold. Crews overwinter at stations with no possibility of evacuation until spring. For field teams operating far from established bases, this isolation is amplified. Emergency medical evacuation in winter is virtually impossible. Knowing this influences decision-making. Certain interior regions are avoided during specific seasons simply because rescue options are non-existent. There are also scientific priorities to consider. Research funding is finite. Deploying teams to extremely remote areas with high logistical costs must be justified by expected scientific return. Some regions near the South Pole offer minimal incremental data compared to more accessible sites. Until technology improves or new questions arise, those areas remain lower priority. From above, satellites have mapped much of Antarctica with remarkable detail. Ice-penetrating radar reveals subglacial mountain ranges, including the Gamburtsev Mountains buried beneath the East Antarctic ice sheet. These discoveries show that the continent is not a flat slab of ice, but a complex geological landscape concealed by frozen layers. Some areas identified through remote sensing have yet to be visited on the ground, not because they are forbidden, but because reaching them would require multi-year logistical planning. When people hear that scientists avoid certain areas, imagination often fills in the gaps. Speculation thrives in empty spaces. The human mind dislikes unanswered questions, but often the explanation is more practical than dramatic. Extreme cold, shifting ice, funding constraints, environmental protection, risk assessment. That said, Antarctica remains one of the least understood continents in certain respects. Ice cores extracted from deep drilling projects reveal climate records stretching back hundreds of thousands of years. Air bubbles trapped in ice preserve ancient atmospheres. These records are invaluable for understanding climate change. Some areas near the South Pole contain ice so old and so undisturbed that scientists are cautious about drilling too aggressively. The data contained within those layers must be retrieved carefully without compromising structural integrity. Underneath the ice sheet, geothermal heat varies. In some regions, heat flux from the Earth's interior affects ice movement. Subglacial volcanic activity has been detected in parts of West Antarctica. These geothermal influences can create unstable basal conditions. Mapping them requires sophisticated equipment and coordinated international efforts. There are also zones near the pole where ice flow patterns are not fully mapped. Ice streams, fast-moving channels within the ice sheet, can shift over time. Setting up long-term installations in areas with uncertain flow dynamics is risky. Structures could become destabilized over years or even decades. Even aviation presents unique challenges. Near the geographic South Pole, all longitudinal lines converge. Navigation systems must account for this convergence. Aircraft approaching the pole cannot rely on conventional directional references alone. Runways built on compacted snow must be maintained constantly. In more remote interior areas without prepared runways, landing is possible only with ski-equipped aircraft under ideal conditions. Sometimes, ideal conditions simply do not align with research schedules. As you sit wherever you are, perhaps in a warm room with controlled temperature and stable lighting, consider how many variables in your environment remain constant. Electricity flows, internet connects, weather is forecasted accurately days in advance. In Antarctica, particularly near the South Pole, predictability decreases. Systems fail, plans adjust, nature sets the pace. This does not mean scientists are afraid to explore. On the contrary, Antarctic research represents some of the most dedicated and technically sophisticated fieldwork on Earth, but dedication is balanced with caution. Risk is weighed against value. Some areas are left for later, when tools improve, when funding allows, when environmental impact can be minimized further, and there is something else worth acknowledging. In a world where satellites image nearly every square kilometre of the planet, Antarctica still retains a degree of physical remoteness. Not conceptual mystery, but physical inaccessibility. Certain regions remain rarely visited simply because reaching them requires effort beyond current necessity. This pattern has historical precedent. Early Antarctic explorers, like Roald Amundsen and Robert Falcon Scott, faced unimaginable hardships reaching the pole itself. Today's researchers operate with far more advanced equipment, but the underlying environment has not softened. It remains indifferent to human schedules. As we continue to move deeper into this topic, it becomes clear that avoidance near the South Pole is rarely about secrecy. It is about survival, preservation, cost, and timing. Each of these factors intersects with geography, climate, politics, and science in ways that are not immediately visible from a simple map. And once you understand the terrain beneath the ice, the movement of glaciers, the limitations of machinery, and the fragility of isolated ecosystems, the idea of selective exploration begins to make practical sense, because sometimes the most responsible scientific decision is not to rush forward, but to wait, observe, refine methods, and return when the conditions are right. When most people picture the area around the South Pole, they imagine something uncomplicated. A flat white surface stretching in every direction. No trees, no cities, no wildlife moving in herds across the horizon. Just ice and sky. It seems like the kind of place that could be described in a single sentence. Cold, empty, still. And in a way, that simplicity is real. If you stood at the geographic South Pole itself, you would see very little variation. The land does not rise dramatically into peaks. There are no visible rock formations breaking through the snow in the immediate vicinity. The horizon forms a near-perfect circle. It feels minimal, almost abstract, as if someone erased the details from a map and left only white space behind. But that apparent simplicity is misleading. The Antarctic interior, particularly near the South Pole, is not a frozen parking lot. It is an active, shifting, layered system that only appears smooth from a distance. Beneath the surface lies an ice sheet that is thousands of meters thick, slowly flowing under its own weight. Under that ice sheet lies a hidden continent of mountains, valleys, subglacial lakes, and geothermal heat sources. Above it all, an atmosphere so cold and dry that it behaves differently from almost anywhere else on Earth. From far away it looks quiet. Up close, it is complex. The first illusion is flatness. Yes, the surface near the pole appears level, but that level surface is part of a dome. Antarctica's interior rises gradually toward the pole because the ice sheet is thickest there. The South Pole sits at an elevation of roughly 2,835 meters above sea level. That means standing at the pole feels more like standing on a high plateau than at sea level. The air is thinner, oxygen levels are lower. Combined with extreme cold, this elevation adds physiological stress to anyone working there. Even breathing becomes part of the equation. The second illusion is stability. When you see a broad white field, it suggests solidity. But the Antarctic ice sheet is not static. It flows outward from the high interior toward the coasts under immense pressure. The movement is slow, often just a few meters per year near the pole, but it is constant. That means nothing built there is anchored to bedrock. Research stations, markers, even the ceremonial South Pole sign, all move gradually with the ice. Every year, the geographic marker has to be repositioned to reflect the actual location of the pole. The ice beneath it is never still. If you travel away from established stations into more remote interior areas, this subtle motion becomes more significant. Glacial flow can create stress patterns in the ice, leading to fractures and crevasse fields. From above, these areas may appear smooth. But beneath thin layers of wind-packed snow, the ice may be split open into deep cracks. A crevasse can be narrow at the surface and widen dramatically below. Some extend down tens of meters. Falling into one in a remote region is not a minor inconvenience. It can be fatal. Rescue operations in Antarctica are complicated even under favourable conditions. In isolated interior areas, response times can be severely delayed by weather and distance. So the surface that looks simple is, in reality, unpredictable. Then there is light. Antarctica does not experience day and night near the pole in the way most places do. During summer, the sun circles the horizon without setting. During winter, it remains below the horizon for months. This creates extended periods of continuous daylight or darkness. Continuous daylight can distort depth perception. With the sun low on the horizon, shadows stretch long and subtle changes in terrain become difficult to interpret. In whiteout conditions, clouds blend with the snow-covered ground, removing all contrast. There is no visible horizon, no visual cues to determine slope or direction. People describe it as walking inside a ping-pong ball. In such conditions, even experienced field researchers rely heavily on instruments. And instruments, in extreme cold, are not infallible. The cold itself complicates what seems simple. Temperatures near the South Pole can drop below -60 degrees Celsius in winter. At these temperatures, materials behave differently. Plastic becomes brittle, rubber stiffens, Fuel thickens, metal contracts, electrical systems require insulation and heating just to function reliably. It is easy to assume that modern technology can handle these extremes, and in many cases it can. But equipment designed for temperate climates often needs modification before it can survive polar conditions. Batteries lose capacity rapidly in extreme cold. Lithium-ion batteries, common in modern electronics, can lose more than half their effective charge at very low temperatures. In more remote regions near the pole, where recharging stations and backup systems are unavailable, energy management becomes critical. A single failure can cascade into larger problems. Now consider communication. In most inhabited regions of the world, mobile networks, satellite links and radio systems provide multiple layers of redundancy. Near the South Pole, communication relies heavily on satellite coverage that is limited by orbital geometry. Some geostationary satellites sit too low on the horizon to provide stable signals. Specialized polar orbiting satellites help bridge the gap, but bandwidth is limited. In certain interior areas beyond established research stations, communication can be intermittent. This does not mean silence, but it means vulnerability. A storm can interrupt signals. A damaged antenna can isolate a team until repairs are made. When you combine thin air, shifting ice, extreme cold, limited communication, and vast distances, the simplicity begins to fade. Another factor that complicates the apparent emptiness is what lies beneath the ice. The Antarctic continent is not a uniform slab of rock. It contains mountain ranges, ancient river systems, subglacial lakes, and geothermal regions. Radar surveys have revealed features like the Gamburtsev subglacial mountains, a massive mountain range buried beneath kilometers of ice in East Antarctica. These mountains are comparable in scale to the Alps, yet they are completely hidden. Over time, the weight of the ice sheet presses down on the continent, influencing tectonic stress and geothermal heat flow. In some areas, geothermal heat from below interacts with the base of the ice sheet, creating zones where the ice is warmer and more prone to sliding. These basal conditions can alter ice flow patterns in ways that are not fully predictable. For scientists planning expeditions, this means that areas which appear identical from satellite images may behave very differently underfoot. Subglacial lakes add another layer of complexity. These bodies of liquid water remain unfrozen due to pressure and geothermal heat. They are sealed beneath thick ice, isolated from the surface environment for hundreds of thousands of years. Drilling into these lakes is not a straightforward task. Contamination risks are significant. Introducing modern microbes into a pristine subglacial ecosystem could irreversibly alter it. Because of this, certain regions near known or suspected subglacial lakes are approached cautiously. Access requires specialized sterile drilling systems. Until those systems are ready, some areas remain unvisited. Then there is wind. Antarctica is the windiest continent on Earth. Katabatic winds form when cold, dense air descends from the elevated interior toward the coast. These winds can accelerate significantly over long slopes. Even near the South Pole, where slopes are gentle, wind can still reach high speeds. Wind reshapes the surface constantly. Snowdrifts form and shift. Hard-packed surfaces can become soft overnight. Tracks left by vehicles can disappear within hours. Navigation markers can be buried. This continuous reshaping means that a route considered safe one season may require reassessment the next. Isolation adds psychological strain to physical challenges. In interior regions far from stations, teams operate with limited support. Emergency evacuation may not be possible during winter. Aircraft cannot land in complete darkness or extreme cold. Storm systems can ground flights for days or weeks. Knowing that help is distant changes risk tolerance. Even minor injuries must be treated with heightened caution. Equipment redundancy becomes essential. Decision-making becomes conservative. From a distance, the region seems uncomplicated because it lacks visible diversity. No forests, no rivers flowing openly, no visible animals crossing the horizon. But that lack of surface features does not equate to simplicity. It masks underlying systems that are dynamic and interdependent. Even navigation is conceptually unusual at the pole. All longitudinal lines converge there. Walking in any direction is technically walking north. Traditional directional concepts become abstract. GPS systems function, but magnetic compasses are unreliable because the magnetic South Pole is located far from the geographic South Pole and shifts over time. In remote areas without clear landmarks, maintaining orientation requires discipline and constant verification. Funding and logistics also shape what is explored and what is avoided. Antarctica is governed by international agreements under the Antarctic Treaty System. Scientific missions are planned years in advance. Resources are finite. Every expedition requires aircraft time, fuel shipments, personnel support, and emergency contingency planning. If a region offers limited new data relative to cost and risk, it may remain unvisited for years. This is not secrecy. It is prioritization. There is also environmental protection. Certain zones are designated as Antarctic Specially Protected Areas. Entry requires permits. Some areas are restricted because they contain unique geological formations, rare microbial ecosystems, or historical sites from early expeditions. Preservation often outweighs curiosity, and yet, the human mind continues to imagine that emptiness equals mystery. When people hear that scientists avoid certain areas, it invites speculation. But often the explanation is grounded in practical constraints rather than hidden discoveries. Still, there is something quietly compelling about a place that looks so straightforward and turns out to be layered with complication. Imagine standing there. No visible movement except drifting snow. No sound except wind against fabric. Beneath your boots, ice that has been accumulating for millennia. Beneath that ice, mountains and lakes untouched by sunlight. It is not dramatic in appearance. It does not announce its complexity loudly, but it demands respect. A place that should be simple turns out to be one of the most technically demanding environments on Earth. It resists shortcuts. It punishes assumptions. It forces preparation. And once you begin to understand how much is happening beneath that smooth white surface, the idea that some areas remain unvisited begins to feel less like mystery and more like acknowledgement. Not everything that looks open is easily accessible. Not every blank space on a map is empty in the way we imagine. The South Pole region teaches that surface impressions are often incomplete. What appears uniform can conceal variability. What seems still can be moving. What looks harmless can require meticulous planning, and with that understanding the ice begins to look different. Not dramatic, not theatrical, but quietly intricate. A landscape that rewards patience and careful study rather than impulse. Because sometimes the most complex systems are the ones that hide beneath surfaces that appear, at first glance, perfectly plain. If you look at a globe and let your finger drift down toward the very bottom, you'll notice something almost symmetrical about it. Continents cluster in the north, oceans dominate the middle, and then, alone at the base, there is Antarctica. A nearly circular landmass wrapped tightly around the South Pole, separated from every other continent by thousands of kilometres of ocean. It is not just cold. It is not just icy. It is isolated in a way that no other major landmass on Earth is isolated. That isolation begins with water. The Southern Ocean surrounds Antarctica completely, forming a barrier of distance and turbulence. The Antarctic circumpolar current flows endlessly from west to east, driven by strong westerly winds. It is the most powerful ocean current on the planet. It does not encounter continents to break its path. It circles the globe uninterrupted. For ships travelling south, this current is not a gentle drift. It is a force. Waves can reach towering heights. Storm systems roll through with little resistance. Even in modern vessels, the journey is not trivial. And that is before reaching the sea ice, that expands outward from the continent during winter, sometimes doubling Antarctica's effective footprint. So even before one sets foot on the ice, the geography has already imposed its first filter. Then there is scale. Antarctica covers about 14 million square kilometres. That makes it larger than Europe. Yet unlike Europe, there are no roads connecting settlements, no cities scattered across valleys, no railways threading through mountain passes. There are research stations, yes, but they are few and separated by immense distances. The South Pole sits roughly 1,300 kilometres from the nearest coastline. That is farther than the distance from Paris to Rome. Except instead of highways and towns between those points, there is only ice. Imagine planning a journey of over 1,000 kilometres across terrain where temperatures can drop below minus 50 degrees Celsius, where there are no fuel stations, no repair shops, no shelter except what you bring with you. Every kilometre must be calculated, every supply weighed. Distance here is not just a number on a map, it is a logistical barrier. The continent itself is divided broadly into East and West Antarctica. East Antarctica is larger, colder, and geologically older. It sits on a craton, a stable piece of ancient continental crust. West Antarctica, by contrast, is more geologically dynamic and includes areas below sea level beneath the ice sheet. Near the South Pole, you're firmly in East Antarctica. The ice sheet here is thick, stable in relative terms, and elevated. The polar plateau stretches outward like a frozen highland. It is often described as featureless, but that featurelessness is part of what makes it isolating. In most landscapes, features guide you, mountains orient you, rivers lead you, forest edges signal change. Near the South Pole, visual reference points are minimal. The horizon is uniform. Subtle changes in slope can be difficult to detect without instruments. Orientation becomes an intellectual exercise rather than an intuitive one. There is also the matter of climate gradients. Coastal Antarctica, while still harsh, experiences relatively milder conditions compared to the interior. Temperatures can hover around minus 10 to minus 20 degrees Celsius in summer. Near the South Pole, summer temperatures often remain below minus 25 degrees Celsius. In winter, they plunge dramatically lower. The polar plateau creates its own microclimate. Cold air pools at high elevations. Katabatic winds descend toward the coast, but the interior can experience periods of eerie stillness broken suddenly by powerful gusts. This combination of elevation, temperature, and wind patterns makes sustained travel in the interior particularly demanding. Air travel offers one solution to geographic isolation, but even that is constrained. Aircraft flying to the South Pole must contend with fuel limitations, unpredictable weather, and the absence of diversion airports. If conditions deteriorate unexpectedly, options are limited. Runways are carved from compacted snow and ice. They require constant maintenance. Visibility must meet strict thresholds. During the Antarctic winter, flights to the pole cease almost entirely. Darkness and extreme cold make operations too risky. That means for several months each year the South Pole Station is physically cut off from the rest of the world. No flights in, no flights out. In more remote areas beyond established runways, aircraft may be able to land on ski-equipped systems if conditions allow. But these landings require clear weather and careful scouting. In certain interior regions, even landing zones are scarce. Now consider ground traverses. Heavy tracked vehicles can transport supplies across the ice sheet. These traverses move slowly, often taking weeks to cover distances that would be trivial by road elsewhere. Crews must survey routes for crevasses. Fuel consumption must be calculated precisely. Any breakdown can halt progress entirely. The further from established supply lines you travel, the more self-sufficient you must be. Isolation is also temporal. The South Pole experiences a single sunrise and a single sunset each year. During winter, darkness persists for months. Temperatures fall. The sky, when clear, reveals stars with exceptional clarity due to the thin, dry atmosphere. But operationally, this darkness complicates everything. In remote areas without permanent infrastructure, winter travel is nearly impossible. The combination of darkness, cold, and weather makes extended fieldwork dangerous. That seasonal isolation compresses research windows. Most field operations occur during the austral summer, roughly November through February. In that brief window, temperatures rise slightly, aircraft can operate more reliably, and daylight is continuous. Even then, storms can interrupt schedules for days. Another layer of geographic isolation comes from ice thickness. In some parts of East Antarctica, near the pole, the ice sheet exceeds 3,000 meters in thickness. Beneath that ice lies bedrock that has not seen sunlight for millions of years. Any geological survey requires ice-penetrating radar or deep drilling. Drilling through kilometers of ice is not a casual endeavor. It requires specialized equipment transported across great distances. Power generation must be sufficient to operate drills in extreme cold. Meltwater management must prevent refreezing in shafts. In certain areas, the bedrock topography remains only partially mapped. Subglacial valleys and ridges influence ice flow patterns in ways that are still being studied. The hidden landscape adds uncertainty to surface travel. There is also geopolitical isolation. Antarctica is governed by the Antarctic Treaty System, signed in 1959. The treaty designates the continent for peaceful scientific use and prohibits military activity. Multiple countries operate research stations, but sovereignty claims are effectively held in abeyance. While cooperation is strong, logistics are managed nationally. Access to certain regions depends on which country has the capacity to support operations there. The South Pole Station, for example, is operated by the United States. Other nations have their own inland stations, such as Concordia Station operated by France and Italy. In remote areas not near established stations, mounting an expedition may require multinational coordination. That coordination takes time. Planning cycles extend years into the future. Environmental impact assessments are required. Permits must be secured. Isolation, in this sense, is administrative as well as physical. Communication infrastructure is limited compared to the rest of the world. While the South Pole Station has satellite links, bandwidth is finite. Remote field camps may rely on portable satellite phones or high-frequency radio systems. Weather can interfere with signals. Equipment can malfunction in extreme cold. Real-time communication, which is taken for granted elsewhere, becomes a managed resource. Even waste management reflects isolation. In Antarctica, strict environmental protocols require that waste be removed from the continent. Field teams must transport all waste back to stations for eventual shipment north. This includes human waste in some cases. Every expedition must account for what it brings and what it removes. There is no leaving behind. Medical isolation is perhaps the most sobering aspect. In most parts of the world, advanced medical care is within hours. Near the South Pole, especially during winter, evacuation may be impossible. Even during summer, weather can delay flights. Medical screenings for overwintering personnel are rigorous. Dental exams are required because a dental emergency in winter could become serious without evacuation options. In remote field sites beyond established stations, the risk compounds. Teams carry medical kits and often include members trained in emergency response. But advanced surgical facilities are not available. This reality influences decisions about which areas are worth entering. Then there is ecological isolation. Antarctica's ecosystems are relatively simple compared to temperate or tropical regions, yet they are finely balanced. Microbial communities exist in snow, ice, and subglacial lakes. Mosses and lichens survive along coastal areas. Seals and penguins inhabit the periphery. In the interior near the South Pole, visible life is minimal. But microbial ecosystems may exist in ice and beneath it. Because these systems have evolved in isolation for long periods, they are of high scientific interest. Paradoxically, that interest can lead to avoidance. Until sterile methods are perfected, Some subglacial regions are left undisturbed to preserve their integrity. All these factors combine to create a geography that resists casual presence. If you were to stand in a temperate field somewhere familiar, you would likely know where the nearest town is. You would know that if something went wrong, assistance would arrive. You would see roads, hear distant traffic, sense connection. Near the South Pole, in remote interior regions, there is none of that. The nearest help may be hundreds of kilometers away. The weather may close in without warning. The surface beneath your feet may conceal fractures. The air itself is thin and biting. Isolation is not simply about being far from other people. It is about being far from redundancy. Redundancy is what makes modern life comfortable. Multiple power grids, backup systems, emergency services. Near the South Pole, redundancy is limited to what you bring. That is why certain areas remain rarely visited. Not because they are forbidden in some dramatic sense, but because reaching them requires overcoming layered barriers of ocean, ice, distance, climate, logistics, and risk. From space, Antarctica appears as a smooth white circle at the bottom of the planet. From within, it is a network of challenges stacked atop one another, and the deeper into the interior you travel, the more those challenges compound. Geography here is not decorative. It dictates possibility. It determines where stations are built, where aircraft can land, where vehicles can traverse, and where scientists decide that for now, observation from a distance is sufficient. Because sometimes isolation is not a mystery. It is a function of physics, climate, and scale. And in a place where the nearest coastline is more than 1,000 kilometers away, that function shapes every decision made on the ice. Stand in a forest and you can measure distance easily. Trees shrink as they recede, shadows define depth, colours separate objects from their surroundings. Even in a desert, dunes cast edges, rocks interrupt the sand, and the sky meets the land in a way that helps your eyes understand scale. Now remove all of that. Near the South Pole, white dominates everything. The ground is white. The sky, when overcast, becomes white. The horizon fades into white. Light reflects in every direction. Contrast disappears. Depth becomes uncertain. What should be simple, seeing where you're going, turns into a cognitive exercise. This is not dramatic exaggeration. It is a well-documented optical challenge known as whiteout. In a whiteout condition, clouds diffuse sunlight evenly across the surface of the snow. Because snow reflects a large percentage of incoming light, shadows vanish. Without shadows, the human visual system loses one of its primary cues for judging terrain. Small ridges and depressions flatten visually. Slopes appear level. The horizon may disappear entirely, blending seamlessly into the sky. Pilots describe it as flying inside a featureless sphere. Ground crews describe it as walking through a blank page. In such conditions, people have stumbled over gentle rises that looked flat, or stepped unexpectedly into shallow depressions that their eyes failed to register. The danger increases when crevasses are present. Even if radar has identified fractures beneath the surface, navigating across a snow bridge in low visibility demands extreme caution. White, in this environment, is not neutral. It conceals. The human brain evolved in environments rich with variation. We rely heavily on contrast to interpret space. The Antarctic interior offers almost none. On clear days, the sun may hang low and circle the horizon without setting. On cloudy days, light scatters uniformly. Either way, visual monotony dominates. There is also the phenomenon of sastrugi. These are wind-carved ridges of snow that can form sharp, uneven patterns across the surface. From a distance, sastrugi may look smooth. Up close, they can be hard, jagged and disruptive to travel. Vehicles driving across them experience constant vibration. On foot, they can twist ankles or create unstable footing. Under whiteout conditions, sastrui can be nearly invisible until you are directly upon them. Light itself behaves differently in Antarctica because of the high albedo of snow. Albedo refers to the proportion of sunlight reflected by a surface. fresh snow can reflect up to 90% of incoming solar radiation. This reflection creates glare that can strain the eyes. Snow blindness, or photokeratitis, occurs when ultraviolet light damages the surface of the eye. It is essentially a sunburn of the cornea. Protective goggles are not optional. Even on overcast days, ultraviolet radiation can penetrate cloud cover and reflect off the snow. But white does not only distort vision, it distorts scale. In landscapes with trees or buildings, the size of objects provides context. Near the South Pole, there are no trees, no buildings except research stations, no distant hills to anchor perspective. A small mound of snow might appear far larger or smaller than it is. People new to the environment often misjudge distances. What appears to be a short walk may turn into a much longer trek. Conversely, distant objects can appear deceptively close in clear air because Antarctica's atmosphere is exceptionally dry and free of particulates. Dry air increases visibility. On a clear day, you may see objects dozens of kilometers away. Without atmospheric haze to soften edges, mountains in other parts of Antarctica can appear startlingly sharp. Near the South Pole, where mountains are buried beneath ice, this effect is less dramatic, but the clarity of air still contributes to depth misperception. White also hides motion. Snow drifts accumulate gradually, reshaping the surface subtly. A crevasse that was safely bridged one season may widen the next. Surface markers placed to indicate safe routes can become buried. Flags that once stood visible above the snow can disappear beneath accumulating layers. Because snowfall in the Antarctic interior is relatively low, accumulation is often driven more by wind redistribution than direct precipitation. Snow can be scoured from one area and deposited in another, altering surface conditions without any new storm passing overhead. An area surveyed and mapped one year must be rechecked the next. The landscape does not remain fixed. Beneath the surface, white hides even more. Ice sheets are layered records of snowfall compacted over time. Each layer may contain tiny air bubbles, volcanic ash particles, or chemical traces that reveal information about Earth's past climate. But those layers are invisible from above. To see them, scientists drill ice cores and analyze the vertical structure. Without drilling, the surface reveals nothing about what lies beneath. Under kilometers of ice near the South Pole, radar surveys have revealed mountain ranges, valleys, and subglacial lakes. But standing on the surface, you would never know. The ground beneath you might be smooth bedrock, a deep basin, or a ridge rising thousands of meters, all concealed by uniform white. This concealment influences decision-making. When planning fieldwork in remote regions, scientists rely on remote sensing data to infer what lies below. Ice-penetrating radar, satellite altimetry, and gravitational measurements provide clues. But ground truthing, physically verifying those interpretations, requires travel across uncertain terrain. The uniform appearance of the surface makes risk assessment more complex. Even sound behaves differently in this environment. Snow absorbs sound efficiently. Without vegetation or structures to reflect noise, sound can feel muted. Wind may dominate the auditory field, but in still conditions there is a distinct quiet. That quiet, combined with visual monotony, can affect perception. People report feeling disoriented even when stationary. With few sensory anchors, the mind has less external information to process. In whiteout conditions, some individuals experience vertigo. Without a visible horizon, the inner ear and visual system may send conflicting signals about orientation. For pilots, this is particularly dangerous. Without instrument reliance, spatial disorientation can occur quickly. Aircraft accidents in polar regions have historically been linked to whiteout and poor visibility. Modern navigation systems reduce risk, but conditions can still challenge even advanced avionics. White also complicates photography and mapping. Cameras struggle with exposure in bright snow conditions. Automatic exposure systems may underexpose or overexpose scenes due to the dominance of white in the frame. Survey markers must be brightly coloured to stand out. In research settings, visual contrast is deliberately introduced. Flags, poles and equipment are often painted red or orange to provide visibility against the snow. But beyond operational challenges, white influences psychological experience. Humans are accustomed to environments rich with variation, colours, textures, movement. Near the South Pole, visual input narrows. Day after day, the same palette dominates. For overwintering crews, months of darkness replace months of white brightness. Both extremes challenge circadian rhythms and mood regulation. Light therapy lamps are used inside stations during winter to simulate daylight. During summer, blackout shades help regulate sleep in continuous daylight. The environment does not adjust to human biology. Humans must adjust to it. White also masks weather changes. Storms can approach gradually without dramatic visual cues. Snowfall may be light but persistent. Wind can lift fine snow particles from the surface, creating ground blizzards without fresh precipitation. Visibility can drop rapidly. A clear horizon can vanish within minutes. In remote field sites, tents must be anchored securely. Equipment must be weighted or buried to prevent loss in wind. Even footprints can fill in quickly, erasing evidence of direction. Navigation in such conditions relies heavily on GPS and pre-established waypoints. Traditional compass navigation is unreliable near the pole because the magnetic South Pole is not located at the geographic South Pole and shifts over time. So orientation depends on satellites orbiting thousands of kilometers above. White, in this context, is not just colour. It is concealment layered upon concealment. It conceals terrain hazards. It conceals geological complexity. It conceals depth perception. It conceals movement. And because it conceals so effectively, caution becomes habitual. Scientists planning to explore remote interior regions must account for the fact that visual inspection alone is insufficient. Radar surveys, satellite imagery, and repeated route checks are standard practice. Even then, unpredictability remains. From afar, Antarctica's whiteness appears peaceful. It is often described as pristine, untouched, pure. But purity does not imply transparency. It implies coverage that smooths over what lies beneath. There is a reason that some areas near the South Pole remain lightly travelled. When the surface offers few visual clues, when hazards may be hidden under thin snow bridges, when weather can erase landmarks, risk multiplies quietly, not dramatically, not with warning sirens, just gradually. And in a place where assistance is distant, gradual risk accumulation is taken seriously. White does not announce danger. It hides it in plain sight. It creates a landscape that looks uniform but behaves variably. A place where what you see is only part of the story. And as we move further into the realities of the Antarctic interior, that concealment becomes not a poetic idea, but a practical factor shaping every decision made on the ice. Cold is easy to describe in numbers. -10 degrees Celsius feels sharp, -20 feels severe, -40 begins to sound extreme. But near the South Pole, winter temperatures can drop below -70 degrees Celsius. Even in summer, the air often hovers around -25 to -35. Those numbers are not just uncomfortable, they change the way matter behaves. In most parts of the world, machines operate within a narrow thermal range. Cars are designed for winters that might reach -20, perhaps -30 in the coldest regions. Consumer electronics assume temperatures close to room level. Even industrial equipment used in Arctic regions is not always rated for the sustained lows of the Antarctic interior. Cold at the South Pole is not occasional. It is continuous. It does not arrive in short bursts. It lingers. At extremely low temperatures, materials contract. Metal shrinks. Rubber stiffens. Plastics become brittle. Lubricants thicken. Electrical resistance changes. Every component inside a machine responds in some way. Consider fuel. diesel fuel begins to gel as temperatures drop. At certain points, wax crystals form within it, thickening the liquid and clogging fuel lines and filters. Special fuel blends are required for Antarctic operations. Even then, vehicles and generators often need to be kept running or housed in heated enclosures to prevent fuel from becoming unusable. A stalled engine in mild weather is an inconvenience. A stalled engine at -50°C can become a serious situation quickly. Hydraulic systems suffer as well. Hydraulic fluid thickens in extreme cold, reducing responsiveness. In heavy equipment used for snow grooming or ice drilling, this can limit functionality. Preheating systems are often necessary before operation. That requires power, which requires fuel, which must itself remain liquid. It becomes a chain of dependencies. Then there are batteries. Chemical reactions slow dramatically in cold environments. Lithium-ion batteries, commonly used in modern devices, lose capacity as temperatures fall. At -20°C, they may retain only a fraction of their nominal charge. At lower temperatures, performance degrades further. In remote field camps, scientists must insulate batteries, sometimes storing them inside clothing or heated containers to maintain function. Instruments powered by batteries can shut down unexpectedly if exposed to the cold for too long. Even something as simple as a camera can fail if its battery drains too quickly. Electronics themselves are not immune. Circuit boards, solder joints, and connectors experience thermal contraction. If materials with different coefficients of expansion are bonded together, stress can develop at connection points. Over time, this can lead to cracks or intermittent failures. Displays can freeze. Liquid crystal displays become sluggish or unreadable. Touchscreens may fail to register input. Keypads can become stiff. In most environments, machines are assumed to function reliably. Near the South Pole, reliability must be engineered carefully and maintained constantly. Aircraft operations illustrate this clearly. Planes flying into the Antarctic interior require specialized maintenance. Hydraulic systems must be protected. Fuel must be conditioned. Tires, if used, must tolerate low temperatures. Often, ski-equipped aircraft are preferred for landing on snow. Before takeoff, engines may need to be preheated. If an aircraft is left exposed in extreme cold without proper preparation, restarting engines can become difficult or impossible. In winter, aircraft rarely operate at the South Pole at all. Darkness and cold combine to create conditions beyond safe operating thresholds. Ground vehicles face similar constraints. Tracked vehicles used for traverses across the ice sheet are built for durability, but even they require constant monitoring. Metal fatigue behaves differently in cold temperatures. Materials that are flexible at moderate temperatures may fracture under stress when brittle. A small crack in a structural component can propagate more rapidly in cold conditions. Engineers must account for this when designing equipment for Antarctic use. Drilling equipment presents another challenge. Ice core drills must function at depth, often hundreds or thousands of meters below the surface. The drilling fluid used to prevent boreholes from collapsing must remain stable at low temperatures. Pumps must operate reliably. Cables must remain flexible. If a drill becomes stuck deep within an ice core hole, recovery is not straightforward. The investment of time and resources is significant. Communication systems are also vulnerable. Antennas exposed to wind and cold can accumulate ice. Connectors may contract, loosening connections. Satellite equipment must be housed carefully. Heating systems within research stations are critical infrastructure. Fuel lines must be insulated. Backup generators must be ready. A heating failure during winter could threaten lives, not just comfort. Water systems illustrate another dimension of cold-related engineering. At the South Pole Station, water is produced by melting snow. That process requires energy. Pipes carrying water must be insulated and sometimes heated to prevent freezing. Wastewater systems must be managed carefully. In remote field camps, snow is often melted manually or with portable systems. If a heating unit fails, access to water becomes limited quickly. Even clothing becomes part of the mechanical equation. Zippers can freeze, fabric stiffens, moisture from breath can freeze on face coverings, forming ice buildup. Gloves reduce dexterity, making fine adjustments to equipment more difficult. Simple tasks require more time, more care, more energy. Cold also affects time perception indirectly through mechanical processes. Watches powered by small batteries may lose accuracy. Mechanical watches can slow if lubricants thicken. GPS units must be kept warm to preserve battery life. Every device carried into the field must be evaluated for its tolerance to extreme cold. There is a reason why some interior regions near the South Pole are approached cautiously. When temperatures are lower than most industrial standards anticipate, redundancy becomes essential. Spare parts must be transported. Backup systems must be available. Repair expertise must accompany equipment. In areas far from established stations, the margin for mechanical error narrows significantly. Imagine a team conducting radar surveys hundreds of kilometers from the South Pole station. They rely on vehicles to move equipment. They rely on generators to power instruments. They rely on communication systems to maintain contact. If a generator fails and cannot be repaired on site, the mission may end prematurely. If a vehicle breaks down beyond repair, extraction may take days. Cold does not need to be dramatic to be dangerous. It degrades systems gradually. It exploits weaknesses in materials. It tests seals and joints and connections. Over time, cumulative stress matters. The design of the Amundsen-Scott South Pole Station reflects these realities. The station is elevated on stilts to prevent burial by drifting snow. Its systems are insulated. Critical components are housed indoors. Maintenance crews operate continuously. Even so, equipment must be monitored carefully. In the broader Antarctic interior, where infrastructure is minimal, mechanical resilience determines feasibility. Research that requires delicate instruments may be postponed until conditions are favourable. Projects that involve extended field presence may be limited to summer months. Certain areas remain unvisited not because they are forbidden, but because the cost of ensuring machine reliability in those regions is currently too high. Cold also affects human-machine interaction. Fine motor skills decline as fingers cool. Reaction times slow. Fatigue increases. A mechanical issue that would be resolved quickly in a workshop may take hours in freezing wind. Precision tasks such as connecting cables or adjusting instruments require patience. There is also the matter of materials storage. Scientific samples must sometimes be kept at stable temperatures. Ironically, the extreme cold can help preserve samples, but handling them requires care. Equipment stored outside may become so cold that bringing it into a heated environment causes condensation, which can damage electronics. Thermal cycling between cold and relatively warmer interiors creates stress. Designing systems for the Antarctic interior means anticipating not only the cold itself, but the transitions between environments. Even something as simple as writing can be affected. Ink can thicken. Pens may stop working. Field notes must sometimes be recorded with pencils. These details accumulate into a broader pattern. Machines built for moderate climates are vulnerable. Machines adapted for polar use require careful planning and maintenance. In regions beyond established supply chains, mechanical failure carries greater consequences. When scientists evaluate whether to explore a remote area near the South Pole, they weigh the scientific value against logistical complexity. If reaching a region requires transporting specialized cold-hardened equipment across hundreds of kilometers of uncertain terrain, and maintaining it in temperatures that push material limits, the decision is not taken lightly. It is not that cold makes exploration impossible, it makes it expensive, demanding, and unforgiving. The cold does not negotiate, it does not allow shortcuts, it does not overlook minor oversights. A gasket that would function adequately in temperate conditions may crack. A cable sheath may stiffen and split. A battery assumed to last 8 hours may last 3. Multiply that uncertainty across every system required for an expedition, and the margin narrows further. In familiar environments, technology feels dependable. In the Antarctic interior, technology must prove itself continuously, and so certain areas remain infrequently visited, not because they hide secrets, but because sustaining machines there requires effort beyond what current priorities justify. Cold reshapes matter. It reshapes planning. It reshapes risk tolerance. In a place where metal contracts and fuel thickens, where batteries fade and plastics snap, exploration depends not only on curiosity, but on engineering that can endure temperatures few other places on Earth demand. And when engineering meets its limits, caution fills the space where ambition might otherwise rush forward. When you stand on solid ground most places in the world, you assume it will remain where it is. Rock does not drift. Concrete does not slide quietly across a continent. Even sand dunes, though shaped by wind, move slowly enough that we do not feel the motion beneath our feet. Near the South Pole, that assumption does not hold. The surface there feels firm. It feels permanent. You can walk across it. You can build on it. You can place a marker in the snow and return a year later to find it still standing. But the ice beneath you is not stationary. It is part of a vast, slow-moving system, flowing outward from the high interior of Antarctica toward the coast under its own immense weight. The Antarctic ice sheet is not frozen in place. It behaves more like an extremely slow river. At the South Pole itself, the ice is nearly 3 kilometers thick. That thickness creates pressure. Ice, under enough pressure, deforms. It does not shatter like brittle glass. It bends, compresses, and creeps. Over time, gravity pulls it outward in all directions from the polar plateau. The movement is subtle. Near the pole, the ice may move roughly 10 meters per year. That is slow enough that you cannot perceive it directly. But it is fast enough that anything built on the surface will gradually drift. The ceremonial pole marking the geographic South Pole is repositioned each year because the ice beneath it moves. The actual geographic coordinate remains fixed relative to Earth's axis, but the ice shifts slightly away. Each New Year's Day, a new marker is placed at the precise location of the pole, and the old one joins a line of previous markers drifting slowly across the snow. That simple ritual reveals something important. The ground beneath you is in motion, even when it feels still. This movement is not uniform across the continent. Some regions of Antarctica contain ice streams, fast-moving corridors within the larger ice sheet. These ice streams can move hundreds of meters per year. They are driven by complex interactions between ice thickness, bedrock topography, basal water, and geothermal heat. Near the South Pole, the motion is slower, but it is continuous, and continuous movement creates stress. As ice flows over uneven bedrock hidden far below, it stretches and compresses. Where tension exceeds the strength of the ice, fractures form. Crevasses open. Some are obvious, yawning cracks visible at the surface. Others are concealed by thin bridges of snow that drift across the gap and freeze in place. From above, a crevasse field may look like any other patch of snow. The depth of these crevasses can be significant. Some descend tens of meters. In certain regions, especially where ice begins to accelerate toward the coast, crevasse fields become dense and chaotic. Even in the relatively slow-moving interior near the pole, crevasses exist. Routes for vehicle traverses are surveyed carefully using ground-penetrating radar. Teams move cautiously, often roped together when travelling on foot in suspect areas. Because what appears to be a stable surface may conceal emptiness beneath. Ice movement also influences surface topography in ways that are not immediately visible. Subtle undulations in the ice sheet reflect variations in bedrock thousands of meters below. A ridge beneath the ice can create a gentle rise at the surface. A subglacial valley can form a shallow depression. These features are often too gradual to notice without instruments, but they matter. They influence wind patterns, snow accumulation, and ice flow direction. The Antarctic interior is not a static slab. It is a dynamic system responding to gravity, pressure, and temperature gradients. Temperature itself plays a role in movement. At the surface near the South Pole, ice temperatures are extremely low, but deeper within the ice sheet, pressure increases temperature slightly. At the base of the ice sheet, where pressure is greatest, temperatures can approach the melting point of ice. In some areas, basal melting occurs. Thin layers of water form between the ice and the bedrock. That water acts as a lubricant, allowing sections of the ice sheet to slide more rapidly. Subglacial lakes, trapped beneath kilometres of ice, are part of this system. These lakes are not static pools. Some fill and drain over time as water moves through channels beneath the ice. When subglacial water shifts, it can subtly alter ice flow patterns above. Scientists monitor these movements using satellite measurements and GPS stations anchored into the ice. Even small variations in flow rate are significant for understanding the stability of the ice sheet and its contribution to global sea level. But from a fieldwork perspective, movement introduces uncertainty. Structures built on the ice must account for drift. The Amundsen-Scott South Pole Station, for example, is elevated and modular. It is designed to accommodate gradual movement and snow accumulation. Over time, parts of older stations were buried as drifting snow accumulated and ice shifted. Abandoned structures from early Antarctic expeditions have been swallowed partially or entirely by the ice. Movement also means that fixed maps must be updated. Coordinates shift slightly relative to surface features. Survey markers may drift. Long-term experiments anchored in the ice must be recalibrated. If you were to plant a pole in the snow near the South Pole and leave it for a decade, it would not remain where you left it. Ice movement is not chaotic. It follows physical laws, but it operates on timescales that differ from human intuition. We are accustomed to ground that feels permanent. We build cities that last centuries. In Antarctica's interior, the substrate beneath any structure is flowing, even if slowly. This reality influences decisions about where to establish long-term installations. Some areas are avoided because ice flow patterns are not well understood. Building infrastructure in a region with uncertain basal conditions increases risk. There is also the possibility of ice quakes. As ice shifts and fractures, small seismic events can occur. These are generally minor compared to tectonic earthquakes, but they indicate ongoing stress within the ice sheet. Under the right conditions, large sections of ice can crack dramatically. On ice shelves near the coast, calving events can release massive icebergs. While the South Pole itself is far from coastal ice shelves, the interconnected nature of the ice sheet means that stress propagates across long distances. The interior may seem detached from coastal change, but it is part of the same system. Imagine standing in a place that appears utterly still, knowing that beneath your boots lies a mass of ice thicker than most mountains are tall, slowly deforming and flowing toward the sea. It is not raw. It does not vibrate noticeably, but it moves. That quiet movement complicates travel. Crevasses are not the only hazard. Snow bridges covering crevasses can weaken over time. Seasonal changes in temperature and wind can redistribute snow, altering load-bearing capacity. Routes used successfully one year must be reassessed the next. A field team cannot assume that yesterday's safe path is today's. Ground-penetrating radar helps, but it requires equipment, power, and trained operators. In remote regions, bringing such equipment adds logistical weight. In certain parts of Antarctica, blue ice areas appear where wind has scoured away snow, exposing older, denser ice. These areas can be smoother and more stable, but near the South Pole accumulation patterns differ and blue ice is less common. Most of the interior is covered by wind-packed snow, overlying compacted firn and deeper glacial ice. Firn, the intermediate stage between snow and ice, contains air pockets and can compress under load. Vehicles crossing firn must distribute weight carefully to prevent sinking or cracking through weak layers. Ice that moves beneath you changes how you think about permanence. Even scientific instruments placed into boreholes can shift slightly as the surrounding ice deforms. Data must account for movement. The concept of fixed reference points becomes relative in a landscape that drifts. This is one reason why certain interior regions remain lightly visited. Not because they are forbidden, but because understanding the local ice dynamics requires time and resources. Before committing to extensive fieldwork in an area, scientists must map flow rates, identify crevasse zones, and assess long-term stability. In places where data are sparse, caution prevails. It is easy to imagine Antarctica as frozen in time, but frozen does not mean motionless. The ice sheet has been accumulating and flowing for millions of years. Snow falls, compresses, becomes ice, and joins the outward migration. Eventually, much of it will reach the coast and break off as icebergs or melt into the ocean. The interior feeds the edges continuously. So when you stand near the South Pole, you're not standing on bedrock in the way you would on a mountain. You're standing on a conveyor of ice, moving at a pace too slow to feel, but steady enough to measure. That movement shapes crevasses, influences surface texture, alters navigation routes, and challenges assumptions about stability. And in a place where help is distant and weather is unpredictable, the knowledge that the ground itself is not fixed becomes part of every calculation. It is not dramatic. It does not announce itself loudly. But it is constant, and constant slow movement beneath a landscape that already hides its features under white light adds one more layer to why certain areas near the South Pole are approached with patience rather than haste. Most of us grow up trusting a simple idea. If you hold a compass flat in your hand, the needle will point north. It may wobble slightly before settling, but it will align itself with the Earth's magnetic field. That quiet, dependable motion has guided ships across oceans and hikers across forests for centuries. Near the South Pole, that trust becomes complicated. There are two South Poles that matter here. One is the geographic South Pole, the point where Earth's axis of rotation meets the surface. That is a fixed coordinate defined by planetary mechanics. The other is the magnetic South Pole, the point toward which a compass needle points in the southern hemisphere. They are not in the same place. The magnetic South Pole is not even stationary. It drifts over time, sometimes gradually, sometimes more rapidly. It is currently located far from the geographic South Pole and continues to migrate due to changes in Earth's molten outer core. So if you stand at the geographic South Pole and hold out a compass, the needle does not behave the way intuition suggests. In fact, it becomes almost meaningless. Compasses align with magnetic field lines. Near the magnetic poles, those field lines plunge steeply into the Earth rather than running horizontally. This vertical inclination causes a phenomenon called magnetic dip. A compass needle that works well at mid-latitudes can tilt downwards so steeply that it drags against the housing or becomes unstable. At the geographic South Pole, all lines of longitude converge. Every direction is north. If you take a step in any horizontal direction, you are technically walking northward from the pole. East and west lose their usual meaning. In such a place, a compass cannot provide conventional orientation. This has practical consequences. Modern Antarctic expeditions rely primarily on GPS for navigation. Satellite positioning systems provide accurate coordinates regardless of magnetic field behaviour. But GPS devices require power, and power requires batteries, which are affected by cold. Redundancy is essential. If electronic systems fail, traditional navigation tools must be available. Near the South Pole, that means understanding grid navigation systems rather than relying on magnetic bearings. To manage this, researchers use what is called a grid north system. Instead of following magnetic north, they define a grid aligned with a chosen meridian, often the Greenwich meridian. Maps are created using this artificial grid so that direction remains consistent across the polar region. It is a reminder that near the pole, even fundamental reference points must be redefined. Magnetic strangeness is not limited to compass behaviour. The Antarctic region is also an area of scientific interest because of its interaction with Earth's magnetosphere. The magnetosphere is the region of space dominated by Earth's magnetic field. It shields the planet from charged particles streaming from the Sun, known as the solar wind. Near the magnetic poles, field lines funnel these particles toward the atmosphere. When solar particles collide with atmospheric gases, they create auroras. In the southern hemisphere, this is known as the aurora australis. At the South Pole, during winter darkness, the aurora can be visible as shifting curtains of green, pink and purple light across the sky. It is not only visually striking, it is also scientifically valuable. Instruments stationed at the pole monitor interactions between solar activity and Earth's magnetic field. During periods of intense solar storms, geomagnetic disturbances can disrupt communication systems and satellite operations. At high latitudes, these effects are amplified. Radio communication in polar regions can experience interference due to ionospheric disturbances. High-frequency radio signals may reflect unpredictably or degrade entirely during geomagnetic storms. For field teams operating in remote interior areas, communication reliability is critical. While satellite systems provide primary connectivity, radio systems serve as backups. Geomagnetic activity adds another variable. The drifting magnetic pole introduces long-term mapping challenges as well. Magnetic declination, the angle between magnetic north and true north, varies by location and changes over time. Maps must account for these variations. In most inhabited regions, declination changes slowly and predictably. Near the poles, changes can be more pronounced. Geophysicists monitor these shifts carefully. Instruments embedded in the ice record subtle variations in Earth's magnetic field. These data help scientists understand processes occurring deep within the planet's core. The Earth's magnetic field is generated by convection currents in the molten iron of the outer core. As that molten material moves, it generates electrical currents, which in turn produce magnetic fields. These fields are not static. They fluctuate, and occasionally, over geological timescales, they reverse entirely. Magnetic reversals have occurred many times in Earth's history. The field weakens, reconfigures, and re-establishes itself in the opposite orientation. These reversals are recorded in volcanic rocks and ocean floor basalts. Studying the magnetic field near the poles provides insight into the stability and behaviour of the geomagnetic system. But from the perspective of someone standing on the ice, the strangeness is immediate and practical. A compass that spins unpredictably is unsettling. Humans are accustomed to stable reference points. When that stability falters, it introduces cognitive strain. Even GPS systems, though independent of magnetic fields, rely on satellites orbiting Earth. Near the poles, satellite geometry can be less optimal because many satellites are positioned in orbits that favour mid-latitudes. Specialised polar orbiting satellites help compensate, but coverage patterns differ from those near the equator. This means that in some remote interior regions, signal strength and satellite availability can fluctuate. Scientists planning extended fieldwork account for this by carrying multiple navigation systems, redundant GPS units, backup batteries, preloaded waypoints, physical flags marking safe routes. Because when orientation tools become unreliable, error margins increase. Magnetic anomalies also exist in certain Antarctic regions. Variations in the composition of bedrock beneath the ice can create localized magnetic deviations. These anomalies are of interest to geologists mapping subglacial terrain. Magnetometer surveys flown over Antarctica detect subtle changes in magnetic field strength that reveal hidden geological structures. These data help identify buried mountain ranges, ancient tectonic boundaries, and volcanic formations. The Gamburtsev subglacial mountains, for example, were mapped in part using magnetic and radar surveys. Without direct visual access to the bedrock, geophysical measurements provide the only clues. In some interior regions near the South Pole, magnetic data are still incomplete. Conducting surveys requires aircraft equipped with sensitive instruments, flying precise patterns across vast expanses of ice. Again, logistic shape exploration. There is also a psychological dimension to magnetic disorientation. In most landscapes, the sun rises in the east and sets in the west. Shadows move predictably. At the South Pole during summer, the sun circles the horizon continuously, maintaining a constant elevation. It does not rise and set daily. Instead, it traces a slow circular path. Combined with unreliable compass readings, this can distort a sense of direction. Field teams rely heavily on routine, markers placed in straight lines, instruments aligned with grid coordinates, checklists to verify bearings. Because in a place where the Earth's magnetic cues are altered and the sun's motion is unfamiliar, the human brain must rely on systems rather than instinct. Magnetic strangeness is not a dramatic hazard, like a crevasse or a storm. It is subtle. It affects orientation and communication. It complicates mapping. It reminds researchers that even fundamental planetary forces behave differently here. For most people, magnetism is invisible and abstract. It is something learned in school, but near the poles its effects are tangible. The aurora dancing overhead is a visible manifestation of magnetic interaction. The compass needle dipping steeply downward is a physical response to field geometry. Radiostatic during a solar storm is an audible consequence of geomagnetic disturbance. These phenomena are not mysterious in the sense of being unexplained. They are well understood scientifically, but they introduce additional complexity to an already demanding environment. In regions where infrastructure is minimal and distance is vast, complexity compounds risk. When scientists decide whether to venture into certain areas near the South Pole, they consider not only terrain and temperature, but also navigation reliability and communication stability. If geomagnetic activity is high, radio systems may degrade. If GPS signals fluctuate, navigation becomes more dependent on physical markers. If magnetic anomalies exist, traditional compass backups are limited in usefulness. Layered together, these factors shape operational planning. The South Pole region is not chaotic. It operates under consistent physical laws, but those laws manifest differently at extreme latitudes. Magnetic field lines converge. The sun circles without setting. Longitudinal lines collapse into a single point. Instruments behave differently. Reference frames must be redefined. And in a landscape already stripped of visual anchors by endless white, the subtle strangeness of magnetism becomes another reason why exploration proceeds methodically rather than impulsively. Because when even north becomes a flexible concept, precision matters more than ever. If you open a detailed map of Antarctica, especially one used for research planning rather than tourism, you will notice something interesting. Scattered across the continent are areas outlined, coded, labelled with designations that sound administrative and calm. Antarctic Specially Protected Area, Antarctic Specially Managed Area, Restricted Zone, Environmental Monitoring Site. They do not come with dramatic warnings. There are no bold letters announcing danger, but they are marked, and not all of them are widely discussed outside scientific or regulatory circles. This is where imagination tends to run ahead of reality. The phrase restricted area often triggers assumptions of secrecy or concealed discovery. But in Antarctica, the explanation is usually far less cinematic and far more procedural. The Antarctic Treaty System governs activities on the continent. Signed in 1959 and entered into force in 1961, the treaty established Antarctica as a place reserved for peaceful purposes and scientific research. Military activity is prohibited, nuclear explosions are banned, territorial claims are set aside. Over time, additional agreements expanded environmental protections. One of the most significant is the Protocol on Environmental Protection to the Antarctic Treaty, adopted in 1991. it designates Antarctica as a natural reserve devoted to peace and science. Under this framework, certain areas are designated for special protection. An Antarctic Specially Protected Area, often abbreviated as ASPA, is created to safeguard unique ecosystems, geological formations, historical sites, or scientific research zones. Entry into an ASPA requires a permit. Activities within it are regulated carefully. These zones exist across the continent, including in regions not far from the South Pole. Why protect empty ice? Because even what appears empty may contain something scientifically valuable. Microbial communities in snow and ice, rare geological exposures where bedrock emerges through the ice, long-term experiments that require minimal human interference. In some cases, zones are marked to prevent contamination. Take subglacial research. Beneath the Antarctic ice sheet lie lakes that have been sealed off from the surface for hundreds of thousands of years. Lake Vostok is the most well known, but there are hundreds of smaller subglacial lakes mapped by radar. When scientists plan to drill into these lakes, they must ensure that the drilling process does not introduce modern microbes. Even trace contamination could alter an ecosystem that has evolved in isolation for immense periods of time. Before sterile drilling systems are perfected and tested, some areas remain untouched. They are marked not because they contain something dangerous, but because they contain something fragile. There are also historical zones. Early expeditions to Antarctica left behind huts, equipment, and supplies. Some of these sites are preserved as historic sites and monuments under the treaty system. They are protected not because they pose risk, but because they represent human history and extreme conditions. Entry into such areas is regulated to prevent degradation. Then there are zones that are marked for logistical reasons. Aircraft approach paths, fuel depots, waste storage sites, or sensitive communication installations may be designated as restricted to ensure safety and minimise interference. Near the South Pole Station, certain areas are controlled because of scientific experiments that require minimal disturbance. For example, large-scale detectors embedded in the ice, such as the IceCube Neutrino Observatory, depend on low levels of background interference. IceCube is a vast array of sensors deployed deep within the Antarctic ice to detect neutrinos, nearly massless particles that pass through Earth almost undisturbed. The sensors are buried in clear ancient ice to detect faint flashes of light, produced when neutrinos interact with atomic nuclei. Above the installation, surface activities are managed carefully. Vibrations, electromagnetic interference, or certain construction activities could affect data quality, so zones around such installations are marked and regulated. There are also environmental monitoring areas where long-term data are collected. Atmospheric sampling sites near the South Pole measure trace gases to track global climate trends. Snow chemistry studies rely on undisturbed accumulation. If vehicles frequently cross a sampling area, the data may be compromised. From an outside perspective, these zones might appear mysterious because they are not advertised widely. But within the scientific community, their purpose is documented and procedural. Still, the perception of unexplained zones persists partly because of the nature of Antarctica itself. It is remote. Few people visit. Even fewer see detailed operational maps. Information is available, but it is specialized. Another category of restricted area involves safety hazards. Crevasse fields mapped but not stabilized may be marked off limits. Regions with unstable ice flow may be designated as no-go zones for routine travel. Such markings may not be visible from satellite imagery or tourist brochures, but they are included in operational planning documents. And then there is seasonal restriction. Some areas are accessible only during summer. In winter, darkness and cold make travel unsafe. These areas are not permanently forbidden, but effectively closed for months at a time. When someone hears that scientists avoid certain areas near the South Pole, it often refers to a combination of these designations: protection, safety, data integrity, logistics. The avoidance is structured, not secretive. Yet there is an interesting psychological layer here. Antarctica occupies a unique place in the human imagination. It is one of the last places on Earth without permanent civilian populations. There are no indigenous communities, no cities, no highways. Because of this, it becomes a canvas for speculation. Online forums circulate theories about hidden structures beneath the ice, secret military bases, lost civilizations, extraterrestrial artifacts. The idea of marked but unexplained zones fits neatly into such narratives. But the documented reality is far more administrative. If you review the official list of Antarctic's specially protected areas, each designation includes a management plan. These plans describe why the area is protected, what activities are permitted, and how monitoring occurs. For example, some areas protect rare moss communities that exist in coastal oases where ice retreats. Others preserve meteorite concentration zones where dark rocks stand out against the ice and are easier to collect for scientific study. Meteorite recovery areas are particularly interesting. Antarctica is one of the best places in the world to find meteorites, because ice flow concentrates them in certain regions known as blue ice fields. As ice moves, embedded meteorites are transported and eventually exposed to surrounding ice sublimits. These zones may be marked to coordinate systematic collection and prevent random disturbance. Near the South Pole, however, blue ice fields are less common, and protection often relates to scientific installations and atmospheric monitoring. There are also temporary exclusion zones created during active research. If a drilling project is underway, the immediate area may be restricted to prevent accidents or contamination. These restrictions may not be permanent, but they are operationally necessary. It is also worth noting that access to Antarctica itself is limited compared to other continents. Tourism exists, but it is mostly coastal. The interior near the South Pole sees very few non-scientific visitors. Because so few people have first-hand experience there, even ordinary administrative designations can appear opaque. Transparency in Antarctic governance is high by international standards. Treaty meetings publish reports. Environmental impact assessments are documented, but the audience for such documents is specialized. So the idea of zones marked but not explained often arises from a gap between public familiarity and technical documentation. That does not mean every question is answered fully. Antarctica is vast, and research is ongoing. Some areas remain poorly studied simply because resources are finite. But poor study is not the same as concealment. In fact, the treaty system emphasizes data sharing. Scientific findings are meant to be exchanged freely among participating nations. Still, the combination of remote geography, limited access, and formal zone designations creates a perception of mystery. If you were to stand on the ice near the South Pole and see a line of flags marking a boundary, you might wonder what lies beyond it. Is it fragile snow, a hidden crevasse field, a scientific instrument array? Often, the answer is simple. Beyond it lies something that requires careful handling. Antarctica's governance model prioritizes prevention over correction. Once an ecosystem is disturbed or contaminated, restoration is nearly impossible in such extreme conditions. Once a long-term atmospheric data set is compromised, the continuity of measurement is broken. So lines are drawn before problems arise. These lines may not be explained in detail to every observer, but within research planning documents, they are described. There is a quiet discipline to how these zones function. No dramatic fences, no guards, just coordinates on a map and an agreement among nations to respect them. In a place where infrastructure is minimal and oversight depends largely on cooperation, that agreement matters. And perhaps that is the most unusual aspect of all. At the bottom of the world, on a continent without a native population or sovereign government in the usual sense, boundaries exist not to divide nations but to protect shared scientific goals. So when you hear that certain areas near the South Pole are marked and avoided, it is less about hidden secrets and more about structured restraint. Because sometimes the most responsible form of exploration is knowing where not to step, and in a landscape that appears empty but contains delicate systems, Those marked zones are not warnings of something dramatic, but reminders that even in the most remote place on Earth, caution shapes curiosity. If you stand on the Antarctic plateau near the South Pole, you're standing on something that appears uncomplicated. A wide, white surface stretching outward in every direction. No visible rock, no visible water, no obvious sign that anything exists beneath your boots except more ice. But that surface is only the top layer of a structure that is, in some places, more than 3 kilometers thick. 3 kilometers of compressed snow, layered year after year, century after century, millennia after millennia, and below that, an entire hidden continent. The Antarctic ice sheet covers about 98% of the land beneath it. That means almost all of the bedrock, mountains, valleys and basins are invisible to the naked eye. Unlike Greenland, where parts of the bedrock are exposed at the edges, much of East Antarctica, where the South Pole sits, is completely buried. If the ice were removed, the shape of the continent would surprise most people. Radar surveys have revealed mountain ranges comparable in scale to the Alps, deeply carved valleys, vast basins that dip below sea level, and ancient geological structures formed long before Antarctica became encased in ice. One of the most striking discoveries was the Gambutsev subglacial mountains. This mountain range lies beneath the East Antarctic ice sheet, buried under thousands of meters of ice. It was discovered not by explorers walking across peaks, but by aircraft flying systematic radar patterns across the ice surface. The radar pulses penetrated downward, bounced off bedrock, and returned data that scientists used to reconstruct the hidden landscape. The result was astonishing. Jagged peaks, deep valleys, a terrain that, if exposed, would rival major mountain systems elsewhere on Earth. And yet, none of it is visible from above. That alone changes how we think about Antarctica. It is not a flat sheet covering a featureless slab. It is a topographically complex continent concealed beneath ice. Near the South Pole, the bedrock is elevated relative to coastal regions, contributing to the thick ice accumulation there. But even in this elevated interior, variations exist. Subtle surface undulations may reflect deep bedrock ridges or depressions. But mountains are only part of the mystery. Perhaps more intriguing are the subglacial lakes. Beneath the ice sheet, under immense pressure, water can remain liquid despite surface temperatures far below freezing. Pressure lowers the melting point of ice slightly, and geothermal heat from the Earth's interior provides additional energy. The result is a network of lakes trapped under kilometers of ice. Lake Vostok is the most famous. Located beneath roughly 4 kilometers of ice in East Antarctica, it is one of the largest subglacial lakes discovered. Radar data first revealed its existence in the 1970s, and further studies confirmed that it had been isolated from the surface for possibly hundreds of thousands, if not millions of years. What might exist in such a lake? Microbial life is one possibility. On Earth, life thrives in extreme environments: deep-sea hydrothermal vents, acidic hot springs, sub-zero brine pockets. The question is not whether life can exist in extreme conditions, but whether it does beneath Antarctic ice. Drilling into Lake Vostok required extraordinary caution. Scientists feared contaminating the lake with modern microbes from drilling equipment. Sterile techniques were developed. Even so, debates continue about how best to explore such environments without compromising them. Lake Vostok is not unique. More than 400 subglacial lakes have been identified across Antarctica. Some are small, others are large enough to rival major freshwater lakes elsewhere. These lakes are not static. Satellite data have shown that some fill and drain over time as water moves through subglacial channels. The ice above them can rise or fall by several meters as water shifts beneath. From the surface, none of this is visible. You could stand above a lake and have no idea that liquid water exists kilometers below your feet. And then there are subglacial rivers. Recent radar surveys have revealed what appears to be a vast network of interconnected waterways beneath parts of the ice sheet. These channels may carry meltwater over long distances before it reaches the ocean. This hidden hydrology influences ice movement. Water at the base of the ice sheet acts as a lubricant, allowing sections to slide more easily. Variations in subglacial water pressure can alter ice flow rates. Understanding this system is critical for predicting how Antarctica will respond to climate change. But mapping it is difficult. Drilling through kilometres of ice is slow and expensive. Radar provides outlines, but not direct sampling. Every expedition into remote interior areas must balance scientific curiosity with logistical feasibility. Beyond water, the bedrock beneath Antarctica holds clues to ancient supercontinents. Antarctica was once part of Gondwana, a massive landmass that included South America, Africa, India, Australia, and Antarctica itself. Geological similarities between these continents help scientists reconstruct plate tectonic history. Rock samples from exposed areas along the coast have revealed shared structures and mineral compositions, but much of East Antarctica's geology remains concealed. Geophysical measurements suggest that parts of East Antarctica are composed of ancient cratonic crust, some of the oldest rock on Earth. Other areas may have been shaped by tectonic collisions and volcanic activity long before the continent froze. There is also evidence of subglacial volcanoes in parts of Antarctica. In West Antarctica especially, volcanic heat influences ice behaviour. Near the South Pole in East Antarctica, volcanic influence is less dramatic, but geothermal heat still plays a role. Heat flow from the Earth's interior is not uniform. Some areas beneath the ice are warmer than others. That warmth affects basal melting and ice dynamics. All of this lies hidden beneath a surface that appears uniform and quiet. The mystery beneath the ice is not dramatic in the sense of being unknown in principle. Scientists have tools, radar, gravimetry, seismic surveys, satellite altimetry, but tools provide indirect insight. Direct observation requires drilling, and drilling through kilometres of ice is a major undertaking. It demands heavy equipment, power generation, sterile protocols, and months of preparation. In regions far from established stations, such operations are even more complex. That is one reason why some interior areas remain only partially explored. The scientific value may be high, but the logistical cost is higher still. There is also a time element. Ice cores extracted from deep drilling projects preserve climate records stretching back hundreds of thousands of years. Air bubbles trapped within the ice contain samples of ancient atmospheres. By analysing these bubbles, scientists reconstruct past carbon dioxide levels, temperature patterns, and volcanic events. In some parts of East Antarctica near the South Pole, the ice may be more than 1 million years old. Locating the oldest ice requires careful modelling of ice flow and accumulation patterns. Scientists are actively searching for sites where extremely old ice can be drilled without distortion from ice movement. Such projects require years of planning. Meanwhile, beneath that ancient ice, the bedrock remains largely unseen. There is something humbling about that. In an age where satellites map every corner of the Earth's surface in high resolution, an entire continental landscape lies hidden below frozen layers. If the ice were removed, Antarctica would look nothing like it does now. Rivers would cut through valleys, mountains would rise sharply, basins would collect water. Instead, everything is smoothed by ice. Mystery often invites speculation, but the real mystery here is geological and biological, not fantastical. What microbial communities survive in subglacial lakes? How do they metabolize in darkness and pressure? How does subglacial water influence ice stability? How old is the oldest preserved ice? These questions drive research. And yet, certain areas remain unvisited because reaching them requires resources that must be justified carefully. It is not that scientists fear what lies beneath the ice, it is that uncovering it must be done methodically. Because once you drill, once you disturb, you cannot undo the intrusion. So in some regions near the South Pole, radar continues to map quietly from above. Satellites continue to measure surface elevation changes, Models continue to simulate ice flow, and beneath the white surface, mountains stand in darkness. Lakes hold liquid water under crushing pressure. Microbes may drift slowly in isolation. The mystery is not theatrical, it is patient, and it waits beneath layers of ice that move, accumulate, and conceal, reminding us that even in a place that appears empty, there is depth beyond what the eye can see. Among all the hidden features beneath Antarctica's ice, few have captured scientific attention quite like Lake Vostok. It lies deep beneath the East Antarctic ice sheet, roughly 250 kilometers from the geographic South Pole. From the surface, there is nothing to suggest its presence. No depression, no visible water, just wind-packed snow and ice stretching toward the horizon. But nearly 4 kilometers below that surface, radar surveys revealed something unexpected decades ago. A vast body of liquid water trapped beneath the ice. Lake Vostok is enormous. Roughly 250 kilometers long and 50 kilometers wide, it rivals some of the largest freshwater lakes in the world, and it has likely been sealed off from direct contact with the atmosphere for hundreds of thousands, possibly millions of years. The idea of a massive, isolated lake beneath kilometers of ice immediately raised scientific possibilities. If water has remained liquid under pressure and geothermal heat for that long, could life exist there? Microbial life adapted to darkness, pressure, and cold? Organisms surviving without sunlight, perhaps using chemical energy instead? Such questions are not speculative in the sense of fantasy. On Earth, life thrives in extreme environments. Microbes exist in deep-sea vents, acidic pools, salt-saturated brines, and sub-zero brine channels within sea ice. The possibility that Lake Vostok might harbour unique microbial ecosystems was not unreasonable, but with that possibility came a problem. How do you explore a lake that has been isolated for immense periods of time without contaminating it? Drilling through 4 kilometers of ice is not a trivial process. Traditional ice drilling methods often use drilling fluids to prevent boreholes from collapsing under pressure. These fluids can contain hydrocarbons or other chemicals. If such fluids were allowed to mix with the water of Lake Vostok, the lake's pristine condition could be altered permanently. The fear was not that Lake Vostok contained something dangerous to humans. The fear was that humans might damage something irreplaceable. The research station above Lake Vostok is operated by Russia. Drilling began decades ago, initially with the goal of retrieving ice cores for climate research. Over time, as radar data confirmed the presence of the lake, drilling efforts approached the boundary between ice and water. International debate intensified. Environmental protocols under the Antarctic Treaty emphasize preventing contamination of fragile ecosystems. Introducing modern microbes into an isolated subglacial lake could alter its chemistry and biology. Even if only microbes from the drilling equipment were introduced, they might compete with or overwhelm native organisms. And because Lake Vostok has been sealed beneath ice for so long, its microbial inhabitants, if they exist, may be uniquely adapted and potentially vulnerable. In the late 1990s and early 2000s, as drilling approached the lake's surface, scientists paused operations to reassess methods. The concern extended beyond Lake Vostok itself. If contamination occurred there, it would set a precedent for how other subglacial lakes were treated. There are hundreds of such lakes beneath Antarctica. Protecting their integrity became a collective responsibility. Eventually, Russian scientists developed a method intended to minimize contamination. Instead of drilling directly into the lake and allowing drilling fluid to enter, they stopped short of the water interface. The idea was that when drilling pressure was reduced, lake water would rise into the borehole due to hydrostatic pressure, freeze in place, and later be sampled from the frozen plug. In 2012, Russian scientists announced that they had reached the surface of Lake Vostok. Samples retrieved from the frozen borehole water were analysed. Reports suggested the presence of bacterial DNA, though debate continues about whether those sequences represented indigenous organisms or contamination from drilling fluids. Scientific scrutiny followed carefully. The fear of contamination was not paranoia. It was grounded in experience. In other parts of the world, contamination has compromised pristine environments. In caves, on remote islands, even in deep-sea vents, human intrusion has altered ecosystems unintentionally. Antarctica's isolation provides a rare opportunity to study environments that have evolved without direct human influence. Once contaminated, that condition cannot be restored. Lake Vostok also became symbolically important for another reason. Subglacial lakes on Earth serve as analogues for environments that may exist beyond our planet. Jupiter's moon Europa and Saturn's moon Enceladus are believed to harbour subsurface oceans beneath thick ice shells. If microbial life exists in such extraterrestrial oceans, studying Lake Vostok could offer insight into how life survives in dark, pressurized, aquatic environments. That parallel heightened caution. If Lake Vostok could teach us about life in extreme isolation, then preserving its natural state was essential. There were additional scientific concerns as well. Lake Vostok's water chemistry is unique. Dissolved gases may be present at high concentrations due to pressure. The water may be supersaturated with oxygen, potentially creating oxidative stress for organisms. Drilling through the ice sheet also risked altering pressure conditions. If the borehole allowed pressure to change significantly, it might affect lake dynamics. Every intervention had to be modelled carefully. In the years following the 2012 breakthrough, analysis of samples continued. Some studies reported microbial sequences suggesting possible life. Others cautioned that contamination during drilling could not be ruled out. The debate underscored how difficult it is to distinguish native organisms from introduced ones when working at such depths. Lake Vostok is not the only subglacial lake of interest. In 2013, a British team successfully drilled into Lake Ellsworth in West Antarctica using a clean hot water drilling system designed specifically to minimise contamination. That effort ultimately failed due to technical difficulties, but it demonstrated how seriously the international scientific community approached sterile access. In 2019, researchers drilled into Lake Mercer, another subglacial lake in West Antarctica, and successfully retrieved water and sediment samples. They reported microbial life in the lake, confirming that life can exist beneath kilometres of ice. These efforts reflect lessons learned from Lake Vostok. The fear of contamination reshaped how subglacial exploration is conducted. It slowed progress, it increased costs, it required new engineering solutions, but it also reinforced a principle. In Antarctica, scientific discovery must be balanced against preservation. Near the South Pole and across the Antarctic interior, certain areas remain lightly visited because of this principle. If a subglacial lake or unique ice formation lies beneath a particular region, scientists may choose to wait until technology allows clean access. Patience becomes part of methodology. From the outside, this caution can look like avoidance. A lake exists beneath the ice, and scientists hesitate to drill into it. But the hesitation is intentional. Lake Vostok represents one of the most extreme environments on Earth. Darkness, pressure, isolation, chemical conditions unlike surface freshwater lakes. To reach it required decades of planning and international debate, and even after reaching it, uncertainty remained. The fear of contamination extends beyond microbes. Human presence brings fuel residues, exhaust particles, physical disturbance. Even the heat generated by drilling equipment can alter ice structure locally. So when evaluating whether to explore a region near the South Pole, scientists ask not only what they might find, but what they might change. Antarctica is not simply a laboratory. It is a record of Earth's past climate, a repository of ancient ecosystems, and a benchmark for understanding planetary processes. Lake Vostok is one example of how that record demands restraint. Standing above the lake, on a surface of wind-sculpted snow, you would see nothing unusual. No water glimmering beneath thin ice, no visible sign of hidden depth. And yet, kilometres below, liquid water may hold clues to biology under isolation. That duality shapes decision-making. Curiosity urges dissent. Responsibility advises caution. So in some regions near the South Pole, drilling programs are postponed until sterile systems are perfected. Access routes are planned carefully to minimize environmental impact. International review panels assess proposals. Lake Vostok became a case study in how exploration can proceed without haste. Because once contamination occurs, there is no reversing it, and in a place that has remained isolated beneath ice for geological timescales, preserving that isolation becomes part of the scientific mission itself. In most places on Earth, night arrives and then it leaves. A few hours of darkness, then sunrise. Even in the depths of winter at high latitudes, there is usually at least a hint of daylight for part of the day. But near the South Pole, winter behaves differently. The sun sets once, and it does not rise again for months. Around late March, the sun dips below the horizon and begins a long absence. Darkness settles over the Antarctic interior and remains until late September. During that time, temperatures fall further. The air becomes even drier. The horizon disappears into blackness, broken only by stars, the faint glow of the moon, and the shifting curtains of the aurora. For those stationed at the South Pole during winter, this is not a short seasonal inconvenience. It is a prolonged environmental condition that shapes daily life. And for teams considering travel into remote interior areas during winter, it becomes a decisive barrier. The silence of long winters is not simply the absence of sound, it is the absence of movement, light, and escape routes. During the austral summer, aircraft can fly to and from the South Pole Station regularly, weather permitting. Supplies arrive, personnel rotate. If an emergency occurs, evacuation is possible under certain conditions. In winter, aircraft operations nearly cease. Temperatures drop so low that hydraulic systems in planes struggle. Fuel management becomes more complex, darkness complicates landing. The combination of extreme cold and limited visibility pushes aviation beyond safe margins. For several months, the South Pole Station becomes physically isolated. The crew that remains through winter knows this in advance. They are selected carefully. Medical screenings are rigorous. Psychological evaluations are part of the process, because once winter sets in, there is no easy exit. In remote areas beyond the main station, winter travel is even more restricted. Field camps that operate during summer are dismantled before winter. Equipment left behind is secured carefully, knowing it will remain unattended for months. Why avoid winter fieldwork in certain areas near the South Pole? Because darkness and cold amplify every risk. Imagine travelling across the ice when there is no daylight at all. Navigation relies entirely on instruments. GPS remains functional, but batteries drain faster in colder temperatures. Headlamps illuminate only small areas ahead. Depth perception is limited. Crevasses, already difficult to detect in daylight, become nearly invisible. Snowfall and wind can erase tracks quickly. Markers can be buried. Orientation becomes a constant task. Even routine maintenance tasks grow more complex. Adjusting equipment with gloved hands under headlamp light in -60-degree temperatures demands patience and endurance. There is also the psychological dimension. Humans are deeply influenced by light cycles. Circadian rhythms regulate sleep, hormone production, and mood. Extended darkness disrupts those rhythms. At the South Pole Station, artificial lighting simulates day-night cycles indoors. Schedules are structured carefully to maintain routine. Exercise facilities, communal meals, and organised activities help maintain mental health. But in smaller remote teams operating away from infrastructure, those supports are minimal. Isolation intensifies in winter. Sound itself changes in extreme cold. Snow absorbs noise, creating a muted environment. Wind can dominate when it blows, but in still conditions the quiet is pronounced. Many overwintering personnel describe the silence as both calming and unsettling. There are no animals moving across the ice near the pole. No trees rustling, no water flowing openly, no distant city hum, only wind, occasionally the low vibration of generators and the faint crack of contracting ice. That quiet can magnify internal thoughts. Psychological studies conducted at Antarctic stations have documented mood fluctuations during winter months. Symptoms may include irritability, sleep disturbances, mild depression, and reduced cognitive performance. These effects are sometimes referred to collectively as winter over syndrome. It is not a clinical diagnosis, but a recognition that prolonged isolation and darkness influence mental state. When planning exploration in remote regions, mental resilience is as important as physical endurance. A mechanical failure in summer may be resolved with relative calm. The same failure in winter, in darkness and extreme cold, can feel more acute. Medical emergencies present a similar challenge. During winter at the South Pole Station, a small medical facility is staffed, but evacuation is nearly impossible. In extreme cases, limited emergency flights have occurred during winter, but these are rare and involve significant risk. In remote interior areas, without permanent medical staff, the stakes are higher. So certain regions are simply not visited during winter. It is not that they become more mysterious in darkness, it is that the margin for error shrinks further. There is also the matter of temperature gradients. In winter, temperatures at the South Pole can fall below -70 degrees Celsius. At such extremes, exposed skin can freeze in less than a minute. Breathing extremely cold air can irritate airways. Equipment becomes more fragile. Fuel management becomes critical. Engines may need to remain running continuously to prevent freezing. Shutting down machinery overnight can make restarting difficult. Field teams must carry additional fuel reserves, insulation, and heating equipment. All of this increases logistical weight. In summer, sunlight provides not only visibility but slight warming. In winter, even that minimal input disappears. The polar night also changes atmospheric conditions. Without solar heating, temperature inversions strengthen. Cold air settles near the surface. Atmospheric stability increases. For astronomers, this creates ideal observing conditions. The South Pole Station hosts telescopes that operate during winter darkness to study cosmic microwave background radiation and other phenomena. But those operations are carefully structured within established infrastructure. Extending such operations into remote, unsupported areas is a different proposition. There is something else about winter at the South Pole that influences planning. Time perception shifts. With no sunrise or sunset to mark daily cycles, days blend together. Clocks become the primary reference. Schedules must be followed intentionally. In remote field work, where routines may already be minimal, maintaining structured time becomes more challenging. The human mind relies on environmental cues to anchor itself. When those cues vanish, discipline replaces instinct. Communication with the outside world also changes in winter. Satellite availability can fluctuate depending on orbital geometry. Bandwidth may be limited. Internet speeds at the South Pole Station are modest compared to most inhabited regions. In smaller camps, communication may be limited to scheduled satellite phone windows. Knowing that contact with the broader world is intermittent influences morale. So when scientists decide which areas near the South Pole to explore and when, winter often represents a boundary. Not because winter hides secrets, but because winter magnifies risk. Darkness conceals surface irregularities. Cold degrades machines further. Isolation becomes complete. It is possible to endure winter at the South Pole. People do it every year. They conduct research, maintain systems, observe the aurora, and wait for the sun to return. But extending that endurance into remote interior zones without infrastructure requires careful justification. The silence of long winters is not dramatic in the sense of storms or crevasses. It is steady, it is patient, it stretches across months, and in that stretch caution deepens. When the sun rises again in late September, casting light across the ice after months of darkness, aircraft return. Field teams mobilise. Movement resumes. The continent opens slightly, but during winter the interior holds still under darkness, and that stillness combined with cold and distance shapes decisions as much as any hidden mountain or buried lake. Because in a place where even daylight can disappear for half the year, timing becomes as important as curiosity. In most parts of the world, risk is measured partly by how quickly help can arrive. A car breaks down and a tow truck is called. A hiker is injured and a rescue team mobilises. A storm disrupts travel and shelters stand within reach. Even in remote mountain ranges or deserts, search and rescue networks exist with aircraft, vehicles and communication systems ready to respond. Near the South Pole, especially in the deep interior beyond established stations, that assumption weakens. There are moments when rescue is delayed, and there are seasons when rescue is not realistically possible at all. The Antarctic interior does not offer redundancy. There are no nearby hospitals, no roads, no neighbouring towns that can dispatch assistance. If a team is operating hundreds of kilometres from the South Pole station, they're effectively self-contained. During the austral summer, evacuation flights can sometimes be arranged. Weather permitting, ski-equipped aircraft may land at prepared sites, but even then, response times depend on visibility, wind and temperature. In winter, aircraft operations near the South Pole nearly cease. Darkness, extreme cold and unpredictable weather close the air corridor for months. If a serious emergency occurs during winter in a remote location, there may be no immediate way out. This reality shapes every decision about where to go and when. Before any field team departs for a remote region near the South Pole, risk assessments are conducted carefully. Medical screenings ensure that personnel are fit for extended isolation. Training includes emergency procedures, crevasse rescue techniques, equipment repair, and first aid. Redundancy is built into planning. Vehicles are equipped with spare parts. Communication systems are doubled. Extra fuel is carried. Food supplies exceed projected needs. Teams are trained to function independently, because once they leave the main station, they carry their own safety margin. Consider a scenario where a vehicle breaks down far from base. In temperate regions, roadside assistance might arrive within hours. In Antarctica, a recovery team may need to mobilise from a station hundreds of kilometres away. Weather conditions could delay departure. Travel across crevasse terrain is slow. Days may pass before assistance arrives. Now consider a medical emergency, a severe injury, a sudden illness requiring surgical intervention. In summer, evacuation might be possible within a day or two under favourable conditions. In winter, evacuation may not be possible at all. There have been rare winter rescue flights to the South Pole Station, but these are exceptional events involving carefully calculated risk and experienced crews. They are not routine. In remote field sites beyond established infrastructure, such rescue operations become even more complex. The phrase, "when rescue is not an option," does not mean abandonment. It means that rescue is uncertain enough to be treated as a last resort rather than a guarantee. This influences exploration boundaries. Some areas near the South Pole are avoided during certain seasons simply because evacuation would be too difficult. The scientific value of a site must outweigh the logistical risk. There is also the issue of communication latency. Satellite communication provides connection to the outside world, but bandwidth may be limited. In an emergency, contacting support is possible, but immediate physical assistance is not. Medical supplies carried into the field are therefore extensive. Teams often include at least one member trained in advanced first aid or wilderness medicine. Protocols for handling injuries are rehearsed. The environment itself compounds injury risk. Frostbite can develop quickly if skin is exposed. Hypothermia is a constant concern. Even minor cuts can become problematic in cold, dry air. Fatigue increases risk. Long hours in extreme conditions reduce reaction time. Because rescue may not be immediate, prevention becomes the primary strategy. Travel routes are scouted carefully for crevasses. Ropes are used when crossing suspect terrain. Vehicles travel in pairs so that one can assist the other if needed. Fuel reserves are calculated with generous margins. Even weather forecasting becomes critical. In Antarctica, weather can change rapidly. A clear sky can give way to blowing snow. Whiteout conditions can reduce visibility to near zero. Temperatures can drop suddenly. If a team is caught far from shelter during deteriorating conditions, they must rely on portable shelters and survival training. Established research stations provide stable infrastructure, heated buildings, medical rooms, backup power. But beyond those stations, shelter may consist of insulated tents designed to withstand high winds. These tents are engineered carefully, but they are not hospitals. The decision to avoid certain remote areas near the South Pole is sometimes rooted in simple arithmetic. Distance divided by speed equals response time. Add weather variability, add mechanical uncertainty, add seasonal darkness. The result may exceed acceptable risk thresholds. There is also institutional memory. Antarctic exploration history includes tragedies. Early expeditions in the early 20th century faced starvation, frostbite, and fatal miscalculations. Even in the modern era, accidents have occurred. Aircraft have crashed in poor visibility. Vehicles have fallen into crevasses. Fires have broken out in stations. Each incident reinforces a culture of caution. It is not fear in a dramatic sense. It is respect for conditions that do not forgive oversight. The Antarctic Treaty System does not require nations to rescue each other's personnel, but cooperation is common. Nearby stations may assist in emergencies when feasible. However, the distances between stations can be vast. Near the South Pole, the nearest major coastal stations are more than 1,000 kilometers away. That distance matters. In summer, large-scale traverses transport supplies across the ice sheet using heavy tracked vehicles. These traverses move slowly but reliably. In an emergency, they could provide support, but they are not rapid response units. Emergency planning in Antarctica often involves scenarios where outside rescue is delayed significantly. This reality influences mental preparation as well. Personnel selected for interior missions are briefed thoroughly. They understand that self-sufficiency is not optional. They must function effectively under pressure without expecting immediate extraction. Because when rescue is uncertain, resilience becomes essential. There is also the financial dimension. Rescue operations in Antarctica are expensive. Mobilizing aircraft, crews, and support personnel across vast distances requires coordination and fuel. Insurance policies for Antarctic expeditions account for potential rescue costs. Commercial expeditions, including private tours or record attempts, must demonstrate contingency plans. Even then, national programs may be reluctant to divert resources for non-scientific rescues. This reinforces a conservative approach to fieldwork planning. If a proposed mission requires operating in a region where evacuation would be extremely difficult and the scientific return is modest, planners may choose to postpone or relocate the effort. Some interior areas remain lightly visited for this reason. It is not that they are inaccessible in principle. It is that the cost of ensuring safety there is high, relative to the immediate benefit. Weather forecasting in Antarctica has improved significantly. Satellite data, automatic weather stations and modelling provide better predictions than in the past, but forecasting remains imperfect. Blowing snow can reduce visibility suddenly. Temperature drops can strain equipment. When rescue is not assured, margins are expanded, travel windows are shortened, personnel numbers are limited, missions are staged carefully. The idea that rescue might not be possible is uncomfortable in a world accustomed to rapid response. But in Antarctica's interior, it is a practical constraint. During winter, the South Pole Station crew lives with this reality daily. If a serious fire were to occur, containment would rely entirely on internal systems. There are no municipal fire departments. If a medical crisis arises that exceeds on-site capability, options are limited until spring. Yet research continues. Observatories operate. Data are collected. life adapts to isolation. But when extending that isolation into more remote, less supported zones, planners ask a simple question. If something goes wrong here, how do we respond? If the answer is uncertain, the mission may wait, and so certain areas near the South Pole remain infrequently visited, not because they hide secrets, or because they are forbidden, but because safety is measured not only by what can be endured, but by what can be recovered from. In a place where distance is vast, weather is volatile, and infrastructure is sparse, rescue is not always immediate. Sometimes it is delayed, and sometimes, for months at a time, it is not an option at all. That knowledge shapes exploration more quietly than any visible barrier. It defines the edge between ambition and prudence on the coldest continent on Earth. When people hear that certain areas near the South Pole are rarely visited, their thoughts sometimes drift towards secrecy of a different kind. Not geological mystery, not environmental caution, but strategic interest, military history, Cold War tension carried quietly to the coldest continent on Earth. Antarctica has never been entirely separate from global politics. The Antarctic Treaty, signed in 1959, is often cited as a model of peaceful international cooperation. It prohibits military activity, nuclear testing, and the disposal of radioactive waste. It sets aside territorial disputes. It promotes scientific exchange. But the treaty itself was shaped by a specific historical moment. The late 1950s were defined by Cold War rivalry between the United States and the Soviet Union. Nuclear arsenals were expanding, space exploration had begun. The geopolitical atmosphere was tense. Antarctica, remote and largely uninhabited, presented both opportunity and concern. Before the treaty was signed, several nations had made territorial claims in Antarctica. The United Kingdom, Norway, France, Australia, New Zealand, Chile and Argentina all claimed portions of the continent. Some claims overlapped. The United States and the Soviet Union did not formally recognize these claims, but they reserved the right to make their own in the future. Against that backdrop, Antarctica could have become another arena of competition. Instead, during the International Geophysical Year of 1957 to 1958, 12 nations collaborated on scientific research in Antarctica. That cooperation laid the groundwork for the Antarctic Treaty. The treaty froze territorial claims and banned military installations. It allowed military personnel and equipment only for peaceful purposes, such as logistical support for scientific missions. But military involvement did not disappear entirely. In the early years of Antarctic exploration during the 20th century, military forces played a role in logistics. Naval vessels transported supplies. Air forces provided reconnaissance flights. Operation High Jump, conducted by the United States Navy in 1946 to 1947, was one of the largest Antarctic expeditions in history. Officially, Operation High Jump aimed to train personnel and test equipment in cold conditions. It involved ships, aircraft, and thousands of personnel. While its objectives were publicly stated as exploratory and scientific, the scale of the operation reflected strategic interest in cold weather capabilities. During the Cold War, understanding how equipment functioned in extreme environments had obvious military implications. Similarly, the Soviet Union established research stations in Antarctica, including Vostok Station, near which Lake Vostok lies. While these stations operated under the framework of scientific research, the presence of rival superpowers on the same continent inevitably carried geopolitical weight. Antarctica's location also holds strategic significance. The South Pole sits at the southern axis of Earth's rotation. Satellite orbits often pass over polar regions. During the Cold War, polar routes were relevant for long-range missile trajectories between the Northern Hemisphere superpowers. Monitoring stations in high latitudes could track satellite movements and atmospheric conditions relevant to defense systems. However, the Antarctic Treaty strictly prohibits military fortifications or weapons testing. Inspections between treaty parties are allowed to ensure compliance. no nation has openly violated the treaty's military provisions. Yet curiosity about Antarctica's strategic value persisted during the Cold War. Part of that curiosity centred on communication and surveillance. The polar ionosphere behaves differently from mid-latitudes, affecting radio wave propagation. Understanding these patterns was relevant for military communications. Scientific research in Antarctica contributed to broader knowledge of atmospheric physics. Another area of interest was nuclear detection. Antarctic stations were used to monitor atmospheric nuclear tests conducted elsewhere in the world. Ice cores extracted from Antarctica contain traces of radioactive isotopes from mid-20th century nuclear explosions. These data help scientists track global dispersion patterns. While not military operations themselves, such monitoring had implications for arms control verification. The shadow of the Cold War extended subtly across the continent. Even if open militarization was prevented, there were also rumours. Operation High Jump, because of its size and relative secrecy at the time, became the subject of conspiracy theories decades later. Claims circulated that the mission encountered hidden bases or advanced technology beneath the ice. There is no credible evidence supporting such narratives. Declassified documents describe logistical objectives, equipment testing, and mapping. But Antarctica's remoteness makes it fertile ground for speculation. The idea that certain zones near the South Pole are avoided for military reasons often surfaces online. In reality, the treaty system requires transparency. Research stations are open to inspection by other treaty nations. Military activity is limited to support roles. Still, during the Cold War, strategic thinking influenced how nations approached polar regions. The United States built the Amundsen-Scott South Pole Station in 1956. The Soviet Union built Vostok Station in 1957. Both were part of the International Geophysical Year. Scientific competition existed alongside cooperation. Each nation sought to demonstrate technological capability. Operating in Antarctica required engineering, logistics, and endurance. But the presence of military logistics units supporting research blurred lines subtly. Aircraft, ships, and equipment were often operated by military personnel. That support continues today in some form. For example, the United States Air National Guard provides airlift support to Antarctic operations under Operation Deep Freeze. This is not militarization of Antarctica, it is logistical assistance under treaty rules, but it reinforces how closely national capabilities and polar research are linked. There is also the question of resources. Antarctica is believed to contain mineral and possibly hydrocarbon resources beneath its ice. The Antarctic Treaty's environmental protocol currently prohibits mineral resource exploitation. This ban can be reviewed in the future, though any changes would require consensus among treaty parties. During the Cold War, speculation about resource potential added another layer of interest. The idea that hidden mineral wealth might lie beneath the ice fueled some geopolitical attention. However, extraction in such extreme conditions remains economically and environmentally impractical. So while military curiosity existed, it was constrained by international agreement. The South Pole itself hosts scientific installations, including the Ice Cube Neutrino Observatory, and telescopes studying cosmic microwave background radiation. These facilities are openly documented and focused on astrophysics and particle physics. No credible evidence suggests hidden military installations near the pole, yet the Cold War legacy lingers in public imagination. Because Antarctica is remote and access is limited, it feels like a place where secrets could exist unnoticed. In practice, however, Antarctic governance depends on transparency. Research findings are published, stations host international teams, inspections are allowed. The treaty system has endured for more than 6 decades, surviving political changes and global tensions. That endurance is unusual in international relations. Still, during periods of heightened global tension, Antarctic presence sometimes draws attention. Nations continue to build and upgrade research stations. Airstrips are extended. Infrastructure improves. These developments are framed as scientific investment, and they are. But they also reflect national commitment to maintaining a voice in Antarctic governance. Presence confers influence. So when certain areas near the South Pole remain lightly visited, military secrecy is not the primary explanation. Environmental protection, logistical cost, and scientific prioritization are more direct factors. However, the Cold War context shaped the early decades of Antarctic development. It influenced how quickly stations were established, how logistics were organized, and how treaty provisions were negotiated. Military curiosity did not override scientific cooperation, but it coexisted with it. Today, Antarctica remains demilitarized in terms of weapons and fortifications. Military personnel operate there in support roles, primarily providing transport and infrastructure support. But the history of global rivalry leaves subtle traces. The fact that Antarctica is governed by treaty rather than sovereignty reflects a compromise born in a tense era. The continent at the bottom of the world became paradoxically a model of restraint. So when people wonder whether certain areas near the South Pole are avoided for strategic reasons, the answer is less dramatic than suspicion suggests. The Cold War cast long shadows across the 20th century. Antarctica felt those shadows too, but it did not become another battlefield. Instead, it became a shared laboratory, and the zones that remain unvisited are more often defined by ice, distance, and preservation than by secrecy. Still, the memory of global rivalry reminds us that even the quietest continent has never been entirely separate from the world beyond its frozen horizon. Beneath the surface of the South Pole, far below the boots of researchers walking across wind-packed snow, there is an instrument unlike almost anything else on Earth. It does not resemble a telescope in the traditional sense. There are no large mirrors pointed at the sky, no rotating domes, no visible dishes scanning the horizon. Instead, it is embedded deep within the ice itself. The IceCube Neutrino Observatory sits at the Amundsen Scott South Pole Station. Its detectors are not housed in a building. They are suspended along cables that descend more than 2 kilometers into the Antarctic ice sheet. Over 5,000 digital optical modules are frozen in place, forming a 3-dimensional grid inside the ice. From above, you would see only a handful of buildings and antennas at the station. The true instrument lies beneath your feet. IceCube is designed to detect neutrinos. Neutrinos are subatomic particles produced in enormous quantities by stars, supernova, black holes, and nuclear reactions. They are incredibly small, nearly massless, and interact only weakly with matter. Trillions of neutrinos pass through your body every second without you ever noticing. That property makes them difficult to study. Unlike photons, which can be reflected by mirrors or captured by sensors relatively easily, neutrinos rarely collide with anything. To detect them, scientists need a large volume of material in which occasional interactions might occur. The Antarctic ice sheet provides that material. The ice at the South Pole is exceptionally clear at depth. Over tens of thousands of years, snow has compacted into ice with very few bubbles or impurities at certain layers. That clarity allows faint flashes of light, known as Cherenkov radiation, to travel through the ice when a neutrino interacts with an atomic nucleus. When such an interaction happens, secondary particles move faster than light can travel through ice. That does not violate physics. Light slows slightly when moving through a medium. The resulting particle motion produces a brief blue flash. The optical modules embedded in the ice detect those flashes. By measuring the timing and intensity of light at different sensors, scientists reconstruct the direction and energy of the original neutrino. It is an extraordinary concept. A telescope made of ice. A detector spanning a cubic kilometre of frozen water. But placing it there was not simple. To deploy IceCube, engineers drilled dozens of holes more than 2 kilometres deep using hot water drilling systems. Heated water was pumped down to melt shafts through the ice. Cables with optical sensors were lowered into the holes before they refroze. Once frozen in place, the detectors became part of the ice sheet itself. There is no retrieving them easily. They are fixed for the lifetime of the experiment. The choice of the South Pole was deliberate. The geographic South Pole offers stable infrastructure, including year-round power and communication through the Amundsen-Scott station. The cold, while harsh for humans and machines, helps preserve electronic stability at depth. The ice is thick enough to provide a large detection volume. Additionally, because neutrinos can pass through Earth, IceCube can use the planet itself as a filter. By looking for neutrinos coming upward through Earth, the detector avoids contamination from other particles that cannot penetrate the planet. So beneath the white surface, a quiet experiment listens for signals from across the universe. It detects neutrinos from distant galaxies, from supernova remnants, from active galactic nuclei where supermassive black holes accelerate matter to extreme energies. In 2013, IceCube announced the detection of high-energy astrophysical neutrinos originating beyond our solar system. It was the first time such neutrinos were observed clearly. That discovery opened a new window on the universe. Yet even this remarkable installation contributes indirectly to why certain areas near the South Pole are managed carefully. IceCube's detectors are sensitive. Vibrations, electromagnetic interference, and surface activity above the array must be controlled. Construction projects near the detector are coordinated to minimize disruption. While the detector occupies a defined footprint beneath the station, its existence reinforces how valuable undisturbed ice can be. The Antarctic interior provides conditions that are difficult to replicate elsewhere. The ice is thick, stable, and relatively free of background noise compared to populated regions. Building a cubic kilometre neutrino detector in a temperate region would be nearly impossible. Urban vibration, geological activity, and limited clear ice would interfere, so Antarctica's remoteness becomes an asset. However, operating such an observatory at the South Pole also highlights logistical constraints. All equipment must be transported thousands of kilometres from ports to the interior. Drilling systems require massive energy input. Generators must function reliably in extreme cold. Once deployed, the sensors must operate continuously. Maintenance is limited to surface electronics. The modules deep in the ice are inaccessible. If a sensor fails, it cannot be replaced easily. So the installation required careful planning and substantial resources. IceCube also symbolises how scientific priorities shape where humans tread. The area around the South Pole Station is developed relative to the rest of Antarctica. Buildings, fuel storage, power generation, communication towers and research facilities cluster there. But beyond that cluster, the ice extends undisturbed for vast distances. When scientists consider establishing new large-scale installations in remote interior areas, they weigh whether existing infrastructure at the pole can support the effort. In many cases, it is more efficient to expand capabilities near established stations rather than create entirely new remote hubs. IceCube itself is being expanded. Plans for IceCube Gen 2 aim to increase the detection volume by deploying additional sensors in deeper or wider configurations. These expansions will occur within the logistical reach of the South Pole Station, so while IceCube demonstrates that advanced science can occur at the pole, it also reinforces the idea that infrastructure concentrates activity. Beyond that infrastructure, the ice remains largely untouched. There is also a deeper conceptual point. IceCube studies particles that travel across the universe, passing through galaxies, stars and planets without interaction. To detect something so elusive, scientists needed an environment that was itself quiet, stable, and largely undisturbed. The Antarctic interior provides that. But to preserve those conditions, activity must be managed. Heavy industrial operations near sensitive detectors are avoided. Drilling outside planned zones is controlled. Vehicle routes are established carefully. So in a subtle way, the presence of a neutrino observatory beneath the ice contributes to structured use of the surrounding landscape. It is not that areas are avoided because of hidden secrets. It is that scientific installations require stable conditions. Ice cube also underscores the scale of the ice sheet itself. 2 kilometers of ice above the sensors, more below in some places, enough mass to shield against most background radiation. Standing at the South Pole, you would not know that beneath you lies one of the world's most advanced astrophysical instruments. And if you walked a few kilometers away into untouched interior, you would see no sign of technology at all. The contrast is stark. Human presence at the South Pole is concentrated and purposeful. Beyond it, nature dominates. So when people ask why certain areas near the South Pole remain lightly visited, the answer includes not only environmental protection and logistics, but also prioritization. Scientific megaprojects like IceCube demand enormous support. That support is anchored at established stations. Extending similar efforts into entirely new interior zones would multiply complexity. Instead, the ice beneath the pole itself becomes the laboratory. The rest of the interior remains largely unmarked, and somewhere beneath that white surface, frozen cables hold sensors that watch for flashes of light, caused by particles that began their journey millions or billions of years ago. A telescope pointed not upward, but inward, into the ice. Quiet, patient, listening. While above, the wind drifts snow across a landscape that still keeps most of its depth hidden from view. Antarctica has a way of inviting imagination. Perhaps it is the scale, a continent larger than Europe. Perhaps it is the remoteness, no permanent cities, no indigenous population, limited access. Or perhaps it is the simple visual fact that most of what exists there lies hidden beneath ice. When a place appears blank on the surface, people tend to project onto it. And so, around the South Pole in particular, theories drift like snow across the internet and popular culture. Some settle briefly before melting under scrutiny. Others accumulate layer upon layer, forming stories that seem solid until examined closely. One of the most persistent themes involves hidden structures beneath the ice. Because radar has revealed mountains and lakes below kilometers of frozen surface, it is not difficult for speculation to extend further. If mountains are hidden, why not cities? If lakes are sealed, why not secret facilities? The logic sounds simple when stated casually, but it does not survive contact with physics or logistics. Drilling through 2 to 4 kilometers of ice requires enormous energy, equipment, and time. IceCube, the neutrino detector at the South Pole, required years of planning and thousands of tons of equipment to deploy sensors deep into the ice. Even that project drilled narrow shafts, not large caverns. Creating a concealed underground complex beneath kilometers of Antarctic ice would demand infrastructure on a scale far exceeding anything that has been documented there. Fuel deliveries, construction equipment, ventilation systems, waste management. Such activity would not be subtle, and Antarctica is not unmonitored. Satellite imagery covers the continent regularly. Research stations from multiple countries operate across it. The Antarctic Treaty permits inspections of stations by other treaty parties. The notion of a vast hidden installation remaining undetected for decades does not align with practical reality, yet the theories persist. Part of the reason is historical ambiguity. Early Antarctic expeditions were often poorly documented by modern standards. Operation High Jump, conducted by the United States Navy in the late 1940s, involved a large fleet and extensive aerial mapping. The scale of that operation has fueled speculation for decades. In reality, its objectives were publicly stated: training personnel in cold conditions, testing equipment, and mapping coastline. But because Antarctica itself is mysterious to many people, large-scale expeditions appear dramatic. Add Cold War tension to that image, and imagination fills in gaps. Another recurring theory suggests that Antarctica conceals ancient civilizations. The argument typically follows a pattern. Antarctica was once part of the supercontinent Gondwana. It was not always covered in ice. Therefore, perhaps advanced cultures existed there before glaciation. Geologically, Antarctica indeed experienced warmer climates millions of years ago. Fossilized forests have been found in parts of the continent. During the Cretaceous period, Antarctica supported vegetation and even dinosaurs. But that was tens of millions of years ago, long before humans existed. Modern humans have been around for roughly 300,000 years. Antarctica's ice sheet has existed in its current form for millions of years. There is no credible archaeological evidence of human civilization predating the ice. Yet maps from the 16th century sometimes feature a southern landmass drawn vaguely, which some interpret as ancient knowledge of Antarctica. In reality, these maps reflect speculative geography common in that era. Cartographers often hypothesized a southern continent to balance the northern landmasses, based on philosophical symmetry rather than exploration. Speculation accumulates because Antarctica is distant enough that most people will never see it firsthand. There are also theories centered on extraterrestrials. The logic again follows concealment, a remote continent, little populated, governed by international treaty. A convenient place, in theory, to hide something extraordinary. But hiding something in Antarctica is not straightforward. The continent's harsh environment makes large-scale construction and maintenance extremely difficult. Supply chains depend on seasonal access. Equipment fails in extreme cold. Rescue is limited. Any sustained secret operation would require visible logistics, and Antarctica is not controlled by a single nation. Dozens of countries operate stations there. Inspectors may visit. Scientific results are shared internationally. The governance model does not lend itself easily to unilateral secrecy. Some theories drift from misinterpretations of scientific data. For example, when satellite imagery reveals unusual shapes beneath ice, perhaps a subglacial mountain ridge or a crevasse pattern, images circulate online labelled as artificial structures. But ice-penetrating radar images are not photographs. They are reconstructions based on reflected signals. Human brains are adept at recognizing patterns, even where none were intended. A ridge becomes a pyramid. A cluster of ridges becomes a city grid. Without context, data can appear suggestive. There is also the psychological element of forbidden space. When people hear that certain areas near the South Pole are restricted or require permits, the mind may leap towards secrecy. In reality, as discussed earlier, many of these zones are protected for environmental or scientific reasons. Subglacial lakes are shielded from contamination. Meteorite fields are managed carefully. Atmospheric sampling sites must remain undisturbed. Restriction does not imply concealment. But in a place already distant from everyday experience, restriction feeds narrative. The internet accelerates this process. A single satellite image can circulate globally within hours. A claim, once made, can be repeated thousands of times before correction spreads. Antarctica's remoteness means few can verify claims personally. So theories accumulate like drifting snow. They layer quietly. Each repetition adds a thin covering. Eventually, the underlying facts become harder to see beneath speculation. There is something understandable about this. Humans are drawn to mystery. Blank spaces on maps once invited exploration. Now that most of the Earth's surface is mapped in detail, Antarctica remains one of the last places where large-scale physical inaccessibility persists. Mystery is compelling. But the real mysteries of Antarctica are scientific, not conspiratorial. How stable is the East Antarctic ice sheet in a warming climate? How does subglacial hydrology influence ice flow? What microbial life exists beneath kilometers of ice? How old is the oldest preserved ice core? These questions lack cinematic flair, but they are profound. Theories that drift like snow often fade when confronted with scale. Consider the logistics of supporting even a modest scientific station at the South Pole. Fuel must be transported across thousands of kilometers. Buildings must be engineered to withstand wind and drifting snow. Waste must be removed from the continent under environmental protocols. Now imagine multiplying that effort in secrecy across vast interior areas. The cost and visibility would be enormous. Moreover, Antarctic research is collaborative. Scientists from different nations publish findings in peer-reviewed journals. Data are shared. Satellite imagery is publicly available. Secrecy is difficult to maintain under such conditions, and yet theories continue. Perhaps because Antarctica feels separate from daily life. Few commercial flights go there. Tourism is limited mostly to the coast. The interior remains the domain of researchers and support personnel. Distance creates narrative space. But distance does not create hidden civilizations or secret bases by default. It creates logistical challenges, environmental constraints, and scientific opportunity. When someone says that scientists avoid certain areas near the South Pole, it is tempting to imagine hidden knowledge. In reality, avoidance often reflects practical reasoning. Crevasse fields, limited rescue capability, protection of fragile ecosystems, budget constraints, seasonal darkness. The reasons are grounded in physics and policy. Theories drift because snow drifts. Wind reshapes the surface, creating patterns that resemble structures. Shadows cast by low sun angles create geometric illusions, but step closer, measure carefully, drill if necessary, and the forms resolve into ice and rock. Antarctica does not need hidden secrets to be extraordinary. It is already a continent with kilometers of ice concealing mountain ranges, a place where neutrino detectors listen for signals from distant galaxies, a region where lakes exist in darkness beneath crushing pressure. That reality is complex enough, and so, while speculation continues to move across screens and conversations like windblown snow, the actual work in Antarctica proceeds methodically. Measuring, drilling, observing, publishing. Quietly, beneath a sky that circles slowly overhead and above ice that keeps most of its depth hidden, without the need for anything more dramatic than geology and time. In 1959, 12 nations signed an agreement that would quietly reshape the bottom of the world. It did not divide territory in the traditional sense. It did not establish a new country. It did not create borders marked by fences or checkpoints. Instead, it set rules. The Antarctic Treaty declared that Antarctica would be used exclusively for peaceful purposes. Military activity was prohibited. Nuclear explosions were banned. Scientific cooperation was encouraged. Territorial claims were neither recognized nor dismissed, but effectively set aside. At first glance, the treaty appears straightforward. It keeps conflict away from a remote continent and promotes research. But beneath its clear language lies something more subtle, unspoken boundaries. These are not lines drawn on maps in bold ink. They are expectations, norms, and constraints that shape behavior without dramatic enforcement mechanisms. To understand why certain areas near the South Pole remain lightly visited, the treaty framework matters. The Antarctic Treaty System has expanded over time. The original agreement was supplemented by conventions on wildlife conservation, marine resource management, and, most significantly, the 1991 Protocol on Environmental Protection. The protocol designates Antarctica as a natural reserve devoted to peace and science. It prohibits mineral resource activities, except for scientific research. It requires environmental impact assessments for planned activities. It establishes protected areas. These provisions are explicit. But there is also a culture of restraint that has developed among treaty nations. For example, while the treaty allows military personnel and equipment for peaceful support purposes, nations are careful to avoid the appearance of militarization. Aircraft operated by military units provide logistical support, but weapons are not deployed. Installations are not fortified. This restraint is partly legal and partly diplomatic. Antarctica operates on consensus. Major decisions require agreement among consultative parties. Any action that appears to push the boundaries of peaceful use risks diplomatic friction. So nations move carefully. Consider infrastructure expansion. If a country proposes building a new station deep in the interior, it must conduct environmental impact assessments. Other treaty parties review the proposal. Questions may be raised about fuel storage, waste management, wildlife disturbance, or cumulative impact. The process does not forbid expansion outright, but it encourages moderation. Over time, this has created an informal balance. Stations cluster in certain regions. The South Pole Station operated by the United States, Vostok Station operated by Russia, Concordia Station operated by France and Italy, a scattering of coastal stations operated by various nations. Vast areas remain without permanent infrastructure. There is no rule that says do not build here. But there is an expectation that development should be justified by scientific need and conducted responsibly. That expectation functions as an unspoken boundary. Another subtle boundary involves resource exploration. The Protocol on Environmental Protection bans mineral resource activities other than scientific research. This ban is robust, but it's not permanent in an absolute sense. It can be reviewed in the future, though changes would require consensus. For now, there is broad agreement that Antarctica should not become a site of mining or drilling for oil. That agreement shapes behaviour beyond explicit prohibition. Geological surveys conducted in Antarctica focus on scientific understanding rather than resource mapping for extraction. Even if valuable minerals exist beneath the ice, pursuing them would violate the spirit and letter of current agreements. So exploration proceeds within scientific parameters. There are also boundaries around tourism. Tourism in Antarctica has grown, particularly along the Antarctic Peninsula. The South Pole itself sees limited tourism, mostly through specialised flights. Tour operators must follow guidelines established by the International Association of Antarctica Tour Operators, IAATO, which works in coordination with treaty principles. Certain areas are off limits to visitors to protect wildlife or scientific sites. Again, these are formal restrictions supported by an informal culture of compliance. Near the South Pole, the unspoken boundaries are influenced heavily by scientific installations. The Amundsen Scott Station is a hub for research. Activities around it are structured carefully to minimise interference with experiments such as the Ice Cube Neutrino Observatory and atmospheric monitoring stations. No law prohibits walking in a particular direction across the ice beyond the station's perimeter, but practical and scientific considerations guide where activity occurs. There is also a boundary shaped by cooperation. Antarctica is unique in that it has no native population and no sovereign government in the usual sense. Governance is collective. If one nation were to act aggressively or unilaterally, it would disrupt a delicate equilibrium. So nations tend to avoid actions that could be interpreted as territorial assertion. Even though territorial claims are frozen, claimants maintain symbolic presence through research stations. However, overt expansion into contested areas is approached cautiously. These dynamics create invisible lines of influence and restraint. Scientific data sharing is another example. The treaty encourages free exchange of information. Research findings are published and shared. Inspections of stations by other treaty parties are allowed to ensure compliance. While not every detail of every project is broadcast widely to the public, the framework discourages secrecy in the traditional geopolitical sense. This does not eliminate speculation, but it reduces the likelihood of hidden military installations or covert operations. The unspoken boundaries are reinforced by mutual interest. Antarctica is valuable as a site for climate research, astrophysics, glaciology and biology. If the continent were militarized or exploited for resources, that scientific value would diminish. So maintaining its current status benefits all participating nations. Still, boundaries exist. Environmental impact assessments often lead to scaling down projects. If a proposed drilling site near the South Pole risks disturbing a sensitive subglacial environment, the plan may be revised. Not because of dramatic prohibition, but because consensus favours caution. There are also operational boundaries driven by budget and logistics. National Antarctic programs operate under financial constraints. Building new infrastructure in remote interior regions is expensive. Fuel must be transported across vast distances. Personnel must be supported year-round or seasonally. So while the treaty does not forbid establishing new bases deep in the interior, cost and cooperative norms act as limiting factors. The result is a continent that remains largely undeveloped. This undevelopment is not accidental. It is the product of legal agreement, environmental ethics, logistical reality, and diplomatic balance. Near the South Pole, you see this clearly. A concentrated cluster of buildings stands at the pole itself. A few inland stations operate elsewhere, but between them stretches thousands of kilometers of ice with no permanent human presence. It would be technically possible to build more. But the treaty culture discourages expansion without clear scientific purpose. Unspoken boundaries also influence behavior during crises. If a nation were to experience a major incident at one of its stations, others would likely assist. Cooperation in emergencies reinforces trust. That trust underpins the entire system. The Antarctic Treaty is often cited as one of the most successful international agreements in history. It has endured through decades of geopolitical change. It has prevented conflict in a region that might otherwise have been contested. But its success depends not only on written articles, but on shared restraint. That restraint explains why Antarctica, including regions near the South Pole, remains largely as it is. Blank spaces on maps persist not because they hide secrets, but because the international community has collectively decided that not every space must be filled. In a world where development often expands rapidly, Antarctica stands as an exception. Its unspoken boundaries are lines of agreement rather than barbed wire, and those lines shape where scientists go, where infrastructure is built, and where ice remains undisturbed beneath the cold, circling sun. If you slice deep into the Antarctic ice sheet layer by layer, what you find is not just frozen water, you find time. Near the South Pole, snow falls in small amounts each year. The interior of Antarctica is technically a desert, receiving very little precipitation compared to most other regions on Earth. But what does fall does not melt. It accumulates. Each year's snowfall compresses the layers beneath it. Over decades, centuries and millennia, loose snow becomes firn, and firn becomes solid glacial ice. That process traps tiny bubbles of air. Those bubbles are samples of ancient atmospheres. When scientists drill ice cores near the South Pole and elsewhere in East Antarctica, they are not simply extracting cylinders of frozen water. They are retrieving vertical timelines. Each meter downward represents older snowfall. Each bubble holds a small pocket of the air that existed when that snow first settled. Some Antarctic ice cores extend back more than 800,000 years. Researchers are currently searching for sites that may preserve ice over 1 million years old. Inside those cores are records of carbon dioxide, methane, nitrous oxide, and other atmospheric gases. By measuring the concentrations of these gases in trapped air bubbles, scientists reconstruct past climate conditions. For example, ice core data show that during ice ages, atmospheric carbon dioxide levels were significantly lower than during interglacial periods. The relationship between greenhouse gases and global temperature becomes clear when plotted across hundreds of thousands of years. This is not theoretical modelling alone. It is direct sampling of ancient air. Near the South Pole, sites are chosen carefully for deep drilling projects. The ice must be thick, stable, and relatively undisturbed by complex flow patterns that could distort layers. Even small variations in ice movement can stretch or compress layers, complicating interpretation, so selecting drilling sites requires extensive radar surveys and modelling. Once drilling begins, it is a slow process. Specialised drills cut narrow cores through kilometres of ice. Each segment is brought to the surface, logged, packaged, and stored at controlled temperatures for transport to laboratories. The cores are analysed in sections. Chemical composition of the ice reveals volcanic eruptions through layers of ash and sulfate deposits. Isotopic ratios of oxygen and hydrogen indicate past temperatures. Dust particles reflect changes in wind patterns and aridity. The ice sheet becomes an archive. One of the most important discoveries from Antarctic ice cores is the tight coupling between greenhouse gas concentrations and global temperature over long time scales. When carbon dioxide levels rose, temperatures rose. When they fell, temperatures fell. The data also show that current atmospheric carbon dioxide levels exceed anything seen in at least the past 800,000 years. That context changes how scientists understand modern climate change, but extracting these records requires preserving the integrity of the ice. Contamination is a concern. Drilling fluids must not alter chemical signals. Handling procedures must prevent modern air from mixing with ancient bubbles. Storage temperatures must remain stable to avoid fracturing or gas loss. This is one reason why certain regions near the South Pole remain lightly visited. If a site is identified as potentially containing extremely old, undisturbed ice, access is managed carefully. Driving heavy vehicles across a site can disturb surface layers. Establishing camps nearby can introduce contamination risks. So before drilling begins, planning is meticulous. There is also the matter of basal conditions. At the base of the ice sheet, pressure and geothermal heat can cause melting. If ice near the bedrock has melted and refrozen multiple times, the original climate record may be disrupted. Scientists seek areas where the base of the ice remains frozen to bedrock, preserving continuous layers. Finding such sites requires geophysical surveys. In East Antarctica, including regions not far from the South Pole, some of the oldest ice is believed to exist because of low snowfall rates and stable conditions. The slower the accumulation, the more compressed the layers become over time. This can make older ice accessible at shallower depths compared to areas with higher snowfall. But low snowfall also means that annual layers are thin and harder to distinguish. Analysing ice cores is not simple. It involves high-resolution measurements of isotopes and gas concentrations. Laboratories must maintain extremely clean conditions. The climate record locked in ice extends beyond gases. Microparticles trapped in ice reveal information about distant deserts and volcanic eruptions. For example, increased dust levels in certain layers correspond to colder, drier glacial periods when wind transported more particles across continents. Large volcanic eruptions leave identifiable chemical signatures in ice layers worldwide. By correlating these signatures, scientists can date events precisely. Ice cores also capture evidence of solar variability through isotopes such as beryllium-10, which forms in the atmosphere when cosmic rays interact with nitrogen and oxygen. So within a column of ice a few centimeters in diameter lies an archive of atmospheric chemistry, temperature, volcanic activity, solar radiation, and even biomass burning. Near the South Pole, long-term atmospheric monitoring stations complement ice core research. Air samples are collected continuously to measure present-day greenhouse gas concentrations. These measurements provide context for interpreting the ice record. The clean air of the Antarctic interior, far from industrial pollution sources, offers a baseline for global atmospheric composition. This combination of ancient and modern records makes the South Pole region scientifically valuable. Because of that value, areas identified as prime drilling sites are treated with care. If heavy infrastructure were developed directly above a site containing 1 million-year-old ice, vibrations and surface disturbance could complicate drilling operations. Fuel spills, even small ones, could contaminate upper layers. So planners often locate support camps at some distance from drilling sites and minimize surface traffic. The ice sheet is not just frozen water, it is data stored in solid form, and once that data are disturbed, they cannot be restored. There is also a long-term perspective. Climate records from Antarctic ice inform global policy discussions. They help scientists understand natural climate variability and how current trends compare. When researchers present evidence that modern carbon dioxide levels exceed natural ranges observed in the ice record, they rely on those carefully preserved cores. So protecting potential future drilling sites is not simply about local caution. It is about preserving global scientific resources. Some interior regions near the South Pole are still being evaluated for deep drilling potential. International collaborations seek to identify the best locations for extracting the oldest ice. These efforts require coordination among nations, funding agencies, and environmental review boards. The Antarctic Treaty Framework supports such collaboration, but it also encourages minimal impact. There is something striking about the idea that beneath a flat white surface lies a vertical archive of Earth's climate stretching back hundreds of thousands of years. If you stand at the South Pole today, the snow beneath your boots may one day become part of that archive. It will compress gradually, trapping the air you breathe now. In a distant future, someone might drill down and analyse that layer. That perspective adds weight to the idea of preservation. Certain areas remain unvisited not because they are forbidden, but because they are valuable in ways that are invisible from the surface. The climate record locked in ice is one of Antarctica's greatest contributions to human knowledge, and protecting it requires restraint. So while satellites scan from above and radar maps hidden bedrock, some of the most important information remains sealed quietly in frozen layers, waiting for careful hands and sterile drills to bring it upward without disturbing the story it holds. If you stand near the South Pole and look outward, you see almost nothing that suggests life. No vegetation, no insects drifting through the air, no birds circling overhead, no mammals crossing the horizon. The Antarctic interior, especially at high elevation near the pole, appears biologically empty. Temperatures plunge far below freezing. The air is extraordinarily dry. Liquid water is absent at the surface. Ultraviolet radiation can be intense during summer. Nutrients are scarce. By most conventional measures, it is an environment hostile to life, and yet, life is there. Not in obvious forms, not walking across the snow or sprouting from the ground, but in microscopic communities embedded within the ice, beneath it, and occasionally in transient films of meltwater during rare summer conditions. The life that exists in Antarctica's interior challenges assumptions about where biology can persist. Microorganisms have been found in surface snow near the South Pole. Bacteria and archaea, carried by wind currents from distant continents or surviving locally, can remain viable even at sub-zero temperatures. Some enter dormant states, reducing metabolic activity to near undetectable levels, waiting for slightly warmer conditions to reactivate. The Antarctic atmosphere is not sterile. Airborne microbes circulate globally. Some settle onto the ice sheet and become part of the surface environment. But more remarkable are the organisms found beneath the ice. Subglacial lakes like Lake Vostok and others discovered by radar surveys are isolated from sunlight. Pressure at their depth is immense. Temperatures hover near freezing, but remain liquid due to pressure and geothermal heat. In Lake Mercer, drilled in West Antarctica, scientists found microbial life in water and sediment samples. These microbes appear to survive using chemical energy sources rather than sunlight. This form of life, known as chemosynthesis, does not rely on photosynthesis. Instead, microbes derive energy from chemical reactions involving compounds such as iron, sulfur, or methane. The existence of such organisms expands the definition of habitable environments. Near the South Pole in East Antarctica, subglacial lakes are numerous. While not all have been sampled directly, radar and modelling suggest similar conditions. It is reasonable to suspect that microbial life may exist in some of these hidden water bodies as well. There are also microbial communities within the ice itself. In certain layers of glacial ice, pockets of liquid brine form due to high salt concentrations. Salt lowers the freezing point of water, allowing thin films of liquid to persist at temperatures well below zero. Within these microscopic brine channels, bacteria can survive. Metabolic rates in such conditions are extremely slow. Cells may divide only once every hundreds or thousands of years. But survival is not dependent on speed. life adapts. Another surprising environment is the snow surface during summer. When sunlight is continuous and temperatures rise slightly, thin layers of snow may experience localized melting during the warmest hours. These melt events are rare and limited near the South Pole, but they can create microhabitats. In coastal Antarctica, algae sometimes bloom on snow surfaces, creating reddish or greenish patches. These are more common along the peninsula, but the principle applies broadly. Where liquid water appears, even briefly, life can take hold. In the deep interior near the pole, such blooms are unlikely due to extreme cold. But microbial traces can still be detected. Even rocks, where exposed in some Antarctic regions, harbour life within tiny pores. These endolithic communities live inside rock surfaces, protected from ultraviolet radiation and extreme temperature fluctuations. Near the South Pole, exposed rock is rare because the ice sheet is so thick. But in other parts of Antarctica, this adaptation is well documented. Life also exists in the atmosphere above Antarctica. Airborne bacteria and fungal spores circulate globally. Some deposit on the ice sheet. Most do not establish stable colonies in the interior due to harsh conditions, but their presence demonstrates the interconnectedness of Earth's biosphere. Perhaps the most compelling reason scientists approach certain interior areas cautiously is precisely because of this life. If microbial ecosystems exist in subglacial lakes that have been isolated for hundreds of thousands of years, contamination from modern organisms could alter them irreversibly. Introducing surface microbes into a sealed subglacial environment could disrupt chemical balances and competitive dynamics. So areas suspected to contain such ecosystems are protected until sterile access methods are developed. There is also the question of resilience. Microbes that survive in Antarctica's interior may hold clues about biochemical adaptations to extreme cold, low nutrients, and high pressure. Enzymes from such organisms can function at low temperatures, making them valuable for biotechnology. Studying these organisms requires careful sampling, because once disturbed, their native conditions cannot be recreated easily. Life near the South Pole does not resemble forests or coral reefs. It is sparse, microscopic, and often dormant. But it is persistent, and that persistence has implications beyond Earth. Astrobiologists study Antarctic subglacial environments as analogues for icy worlds in our solar system. Jupiter's moon Europa and Saturn's moon Enceladus are believed to harbour subsurface oceans beneath thick ice shells. If life can survive beneath kilometres of Antarctic ice without sunlight, it strengthens the case that life might exist in similar extraterrestrial environments. Antarctica becomes a testing ground for methods of sterile exploration. If we cannot drill into a subglacial lake on Earth without contaminating it, how would we drill into an ocean on Europa? So the life that should not exist there, in a place so cold and isolated, becomes scientifically significant. Near the South Pole, the absence of visible ecosystems does not mean biological emptiness. Even the ice cores extracted for climate research contain traces of ancient microorganisms. Some remain viable after being frozen for thousands of years. The concept of dormancy is central here. In extreme cold, metabolic processes slow dramatically. Cells repair damage slowly. Energy use is minimized. Life does not cease entirely. It persists at the edge of activity. This challenges conventional notions of habitability. When people imagine Antarctica, they often think of penguins and seals, but those animals inhabit coastal regions where ocean access provides food. The deep interior near the South Pole is far removed from marine ecosystems. Large animals do not venture there, yet microbial life finds ways to endure. In some cases, microbes metabolize trace gases present in the atmosphere, such as hydrogen and carbon monoxide, extracting minimal energy from sparse resources. These survival strategies are subtle and efficient. Because life exists even in such extremes, environmental protection measures become more complex. An area that appears barren may contain microbial communities invisible to the naked eye, disturbing snow layers, introducing foreign organisms, or altering chemical balances can have consequences. So when scientists avoid certain regions near the South Pole, part of the reason is respect for these unseen ecosystems. It is not that the ice conceals something dramatic in a cinematic sense. It conceals something delicate, life that persists where it seems impossible. The Antarctic interior reminds us that biology is adaptable beyond intuitive limits, and because of that adaptability, caution becomes necessary. If a drilling program introduces microbes into a subglacial lake, distinguishing native organisms from contaminants becomes difficult. If a fuel spill alters surface chemistry, microbial communities may shift. The absence of visible life does not equate to ecological insignificance. In fact, it increases the importance of careful study. Near the South Pole, life does not announce itself loudly. It resides in microscopic films, in brine pockets, in dark lakes under crushing pressure. It survives without sunlight, without warmth, without abundance. And that quiet survival shapes how humans move across the ice. Because even in the coldest, driest, most isolated place on Earth, the surface is not truly empty. It holds organisms that challenge definitions of endurance, and preserving their isolation, until we understand them fully, becomes part of why some areas remain lightly touched by human presence. There is a question that sits quietly behind much of Antarctic research. It is not written in bold letters in grant proposals, it is not spoken dramatically in press conferences, but it exists in planning meetings, in risk assessments, in late-night conversations between colleagues looking at maps of the polar plateau. Is this worth it? Not worth it in terms of curiosity. Curiosity is abundant. Antarctica offers some of the most compelling scientific opportunities on Earth. Climate archives reaching back nearly 1 million years, subglacial lakes sealed off from sunlight, ice thick enough to host neutrino detectors searching the cosmos. The question is about cost, risk, and trade-offs. When scientists consider exploring a remote area near the South Pole, an area far from existing stations, perhaps suspected of containing ancient ice or a hidden subglacial feature, they must weigh the scientific value against logistical burden and environmental impact. Every expedition to Antarctica requires enormous support. Fuel must be transported by ship to coastal stations. From there, supplies move inland by aircraft or overland traverse. Heavy equipment for drilling or radar surveys must be hauled across crevasse-prone terrain. Personnel must be housed, fed, and supported in extreme cold. All of that infrastructure leaves a footprint. Under the Antarctic Treaty's environmental protocol, activities must minimize impact. Waste must be removed. Fuel spills must be prevented. Wildlife disturbance must be avoided. In the interior near the South Pole, wildlife is not a major concern, but contamination of pristine ice, disturbance of long-term monitoring sites, and cumulative environmental effects still matter. So when researchers identify a potential drilling site hundreds of kilometers from established infrastructure, they ask themselves whether the knowledge gained justifies the intrusion. That is the quiet question. It is rarely framed in dramatic language, but it shapes decisions. For example, the search for the oldest ice in Antarctica has led scientists to survey vast regions of East Antarctica. Models suggest that ice, older than 1 million years, may exist in certain areas, where ice flow is slow and basal melting minimal. Finding such ice would extend the climate record further back than ever before. It could help clarify how Earth's climate cycles shifted roughly 1 million years ago from 41,000-year glacial cycles to 100,000-year cycles. The scientific value is high, but drilling through kilometers of ice requires heavy equipment, fuel, and months of work. Establishing a temporary camp at a remote site increases risk, so planning proceeds carefully. Survey flights map potential sites. Radar identifies favourable layering. Environmental assessments evaluate impact. Only then does a drilling campaign move forward. Sometimes, after evaluation, a site is set aside. Perhaps the ice flow modelling reveals distortions. Perhaps logistical constraints make the mission impractical within current budgets. The question remains, is this worth it now? There is also the issue of diminishing returns. Antarctica has been studied intensively for decades. Coastal regions and major interior stations host long-term projects. Adding a new remote site must offer something significantly different to justify its cost. Scientific funding is finite. Resources allocated to one project cannot be used for another, so researchers prioritise. Another dimension of the unspoken question involves human safety. We have already considered how rescue is not always immediate in Antarctica's interior. When a team proposes operating in a particularly remote area near the South Pole, safety margins narrow. Weather unpredictability, mechanical failure in extreme cold, crevasse fields that may shift over time. The scientific payoff must justify exposing personnel to those risks. No one phrases it bluntly, but the calculation exists. Is this dataset worth the possibility of equipment loss, of delayed evacuation, of physical hardship that could have been avoided by focusing on a more accessible site? Scientists are not indifferent to risk. They mitigate it through training and redundancy, but they are aware that Antarctica does not forgive oversight easily. There is also a philosophical layer. Antarctica remains one of the last large-scale environments on Earth where human presence is limited and regulated. Its relative emptiness is part of its value. Each new installation, each new camp, each new traverse route alters that emptiness slightly. Some researchers feel a responsibility to preserve as much of that untouched character as possible. This is not anti-scientific sentiment. It is an awareness that the act of studying a place changes it. Drilling through ancient ice introduces modern equipment. Establishing fuel depots alters surface chemistry. Even footprints in wind-packed snow represent disturbance, however temporary. So the unspoken question becomes, should this area remain as it is, not forever, not necessarily untouched indefinitely, but for now, because some questions can wait. Technology improves over time. Drilling systems become cleaner and more efficient. Remote sensing methods grow more precise. Data modelling becomes more accurate. An area that is difficult to access today may be studied with less impact tomorrow. So sometimes the answer to the quiet question is not no, but not yet. Climate change adds urgency to certain projects. Ice shelves are thinning. Glaciers are accelerating. Sea level rise projections depend on understanding Antarctic ice dynamics. In those cases, the question often tilts toward action. But in other cases, exploring a subtle geological anomaly or mapping a region already broadly understood, the calculus may lean toward restraint. There is also the broader geopolitical context. The Antarctic Treaty has held for decades, but it depends on continued cooperation. Large-scale development in the interior, even for scientific purposes, could shift perceptions. Nations are careful not to appear to claim territory through infrastructure expansion. So the decision to establish a new inland station or major facility is weighed diplomatically as well as scientifically. The unspoken question then has multiple layers. Is it scientifically valuable? Is it logistically feasible? Is it environmentally responsible? Is it diplomatically appropriate? Is it safe? If the answer to any of those is uncertain, projects may be delayed or scaled back. From the outside, it might look like avoidance. Why not explore every corner of the continent? Why leave vast regions near the South Pole lightly visited? Because exploration is not a simple act of curiosity, it is a balance. The Antarctic interior is not empty in a trivial sense. It contains climate records, hidden lakes, microbial ecosystems, and geophysical structures that inform our understanding of Earth and beyond. But it is also fragile in its own way. The snow that falls today may become part of a climate archive studied centuries from now. The ice sheet that hosts neutrino detectors and drilling sites also hosts delicate chemical signals and microbial communities. Scientists rarely stand in front of cameras and say, "We're choosing not to go there." But those choices happen, in planning rooms, in environmental review documents, in budget meetings. Sometimes the most responsible scientific decision is restraint. The unspoken question is not about fear or secrecy, it is about stewardship. In a place as remote and as scientifically valuable as the South Pole region, not every blank space must be filled immediately. Some can remain white on the map, not because they hide something dramatic, but because the act of leaving them undisturbed is itself a deliberate choice. If you imagine standing at the South Pole at the end of a long austral summer, the sun still circling low along the horizon, wind brushing fine snow across the surface, there is a certain quiet that settles in. Not silence in the absolute sense. Generators hum within the station buildings, fabric snaps against poles, boots compress snow with a muted crunch. But beyond the cluster of structures, beyond the marked routes and antenna masts, the ice stretches outward without interruption. No roads, no fences, no visible boundary marking where human presence ends, and the continent resumes its slow, patient existence. It is easy to think of Antarctica as dramatic. Storms, crevasses, subglacial lakes sealed in darkness, neutrino detectors buried deep in the ice. But what defines the South Pole more consistently is stillness. Stillness that is not emptiness. We have moved through the reasons scientists avoid certain areas near the South Pole. The ice that moves beneath your feet, the cold that degrades machines, the magnetic peculiarities that unsettle navigation, the zones protected for environmental and scientific reasons, the long winters when rescue is uncertain, the treaty framework that encourages restraint. Each of these factors adds a layer. None of them are theatrical. None of them suggest hidden fortresses or concealed civilizations. They describe physics, logistics, biology, diplomacy. They describe limits. At the edge of the Earth, limits are clearer than in most places. Distance limits speed, cold limits machinery, darkness limits travel, international agreements limit expansion, environmental ethics limit intrusion, and within those limits, science continues carefully. Deep beneath the ice, detectors listen for neutrinos from distant galaxies. In laboratories far from the continent, researchers analyze air bubbles trapped hundreds of thousands of years ago. On the surface, automated instruments sample the atmosphere, contributing to global climate records. Much of the continent, however, remains as it has been for millennia. If you were to leave the station and travel outward for hundreds of kilometers, you would encounter no cities, no abandoned highways, no industrial scars visible from space, just snow compressing into ice, ice flowing slowly toward the sea. The stillness at the South Pole is not fragile in the way a glass ornament is fragile. It is robust. The ice sheet has endured through ice ages and interglacial periods. It has grown and retreated over geological time, but it is sensitive to change. Modern measurements show shifts in ice mass balance in parts of Antarctica. Glaciers accelerate in some regions, ice shelves thin, sea level responds. The interior near the South Pole remains relatively stable compared to coastal sectors, but it is connected to the same system. So the stillness is not permanent in a static sense. It is a dynamic equilibrium. There is something instructive about that. In many parts of the world, development expands until it meets resistance. Forests are cleared, mountains are tunneled, rivers are dammed. The logic of expansion is familiar. Antarctica represents a counterexample, a continent where presence is negotiated rather than assumed, where infrastructure is concentrated and limited, where vast areas remain unmarked not because they are inaccessible in principle, but because they are left that way deliberately. Standing at the pole, you are equidistant from all directions of longitude. Every step leads north. There is no east or west in the conventional sense. That geographical peculiarity mirrors something broader. At the South Pole, familiar reference points dissolve. Magnetic compasses lose clarity. Day and night collapse into months of light or dark. Maps converge to a single point. The world feels simplified and complicated at the same time. Scientists who work there know that the simplicity is deceptive. Beneath the smooth surface lie mountains, lakes, microbial ecosystems, and layered climate archives. Above, particles from distant galaxies pass through detectors embedded in ice. Between those layers, humans operate carefully. The question of why certain areas remain avoided is not answered by a single factor. It is answered by accumulation. Cold plus distance plus environmental protection plus cost plus international agreement plus scientific prioritization. The result is a continent where movement is intentional. That intentionality creates space for stillness, and that stillness has value. In a world saturated with noise and constant motion, the Antarctic interior remains one of the few places where vast scale meets minimal human footprint. It is not untouched. Stations stand at key points. Aircraft land seasonally. Traverses carve temporary paths across the snow. But compared to the rest of the planet, it is restrained. If you imagine the Earth as a living system spinning quietly through space, the South Pole sits at its lower axis, steady and unadorned. Ice accumulates, snow drifts, light circles and then disappears for months. The aurora shimmers during winter darkness, and far beneath, ancient air waits inside bubbles, holding the memory of atmospheres long gone. Scientists will continue to visit. They will drill, measure, map and publish. They will debate which areas to explore next and which to leave undisturbed a while longer. That balance is ongoing. But for now, at the edge of the Earth, much of the ice remains what it has been for ages. Not secret, not forbidden. Simply distant, cold, and governed by physics more than by ambition. The stillness is not emptiness. It is a condition shaped by choice and constraint. And perhaps that is what defines the South Pole more than anything else. A place where curiosity meets limits, and where leaving something alone can be as deliberate as exploring it. Beyond the station lights, beyond the last flagged route, the horizon curves gently under a sky that circles without hurry. And the ice, moving slowly beneath everything, continues its quiet journey toward the sea.